Chapter 17, Part 2 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj, a short account of the history of mathematics by Rouse, Chapter 17, Leibniz and the Mathematicians of the First Half of the 18th Century, Part 2, The Development of Analysis on the Continent. Leaving for a moment the English mathematicians of the first half of the 18th century, we come to a number of continental writers who barely escape mediocrity, and to whom it will be necessary to devote but few words. Their writings mark the steps by which analytical geometry and the differential and integral calculus were perfected and made familiar to mathematicians. Nearly all of them were pupils of one or other of the two elder Bernoullis, and they were so nearly contemporaries that it is difficult to arrange them chronologically. The most eminent of them are Cramer, Degois, de Montmort, Fagagnon, L'Hopital, Nicole, Perrin, Ricuti, Sarin, and Verignon. L'Hopital. Guillaume François Antoine L'Hopital Marquis de Saint-Mesme, born at Paris in 1661 and died there on February 2, 1704, was among the earliest pupils of John Bernoulli, who in 1691 spent some months at L'Hopital's house in Paris for the purpose of teaching him the new calculus. It seems strange, but it is substantially true that a knowledge of the infinitesimal calculus and the power of using it was then confined to Newton, Leibniz, and the two elder Bernoullis, and it will be noticed that they were the only mathematicians who solved the more difficult problems then proposed as challenges. There was at the time no textbook on the subject, and the credit of putting together the first treatise which explained the principles and use of the method is due to L'Hopital. It was published in 1696 under the title Analyse des infiniment petites. This contains a partial investigation of the limiting value of the ratio of functions which for a certain value of the variable take the indeterminate form 0 over 0. A problem solved by John Bernoulli in 1704. This work had a wide circulation. It brought the differential notation into universal use in France and helped to make it generally known in Europe. A supplement containing a similar treatment of the integral calculus together with the additions of the differential calculus which had been made in the following half century was published at Paris 1754 to 1756 by L. A. de Bougainville. L'Hopital took part in most of the challenges by Leibniz, the Bernoullis, and other continental mathematicians of the time. In particular, he gave a solution of the brachistochrone, and investigated the form of the solid of least resistance of which Newton in the Principia had stated the result. He also wrote a treatise on analytical conics which was published in 1707 and for nearly a century was deemed a standard work on the subject. Verignon. Pierre Verignon, born at Caen in 1654 and died in Paris on December 22, 1722, was an intimate friend of Newton, Leibniz, and the Bernoullis, and after L'Hopital was the earliest and most powerful advocate in France of the use of the differential calculus. He realized the necessity of obtaining a test for examining the convergency of series, but the analytical difficulties were beyond his powers. He simplified the proofs of many of the leading propositions in mechanics, and in 1687 recast the treatment of the subject, basing it on the composition of forces. His works were published at Paris in 1725. For further details, see the Éloge by B. de Fontenelle, Paris, 1766. De Montmort. Pierre Raymond de Montmort, born at Paris on October 27th, 1678, and died there on October 7th, 1719, was interested in the subject of finite differences. He determined in 1713 the sum of n terms of a finite series of the form n choose 1 times a plus n choose 2 times delta a plus n choose 3 times delta squared a, and so on, a theorem which seems to have been independently rediscovered by Christian Goldbach in 1718. Nicole, Francois Nicole, who was born at Paris on December 23, 1683, and died there on January 18, 1758. Was the first to publish a systematic treatise on the finite differences. Taylor had regarded the differential coefficient as the ratio of two infinitesimal differences, as the limiting value of the ratio of two finite differences, a method which is still used by many English writers, though it has been generally abandoned on the continent, and thus had been led to give a sketch of the subject in his Methodus published in 1715. Nicole's Traité du calcul des différences finies was published in 1717. It is a well-arranged book and contains rules both for forming differences and for effecting the summation of given series. Besides this, in 1706 he wrote a book on roulettes, especially spherical epicycloids, and in 1729 and 1731 he published memoirs on Newton's essay on curves of the third degree. Perrin, Antoine Perrin, born at Paris on September 16, 1666, and died there on September 26, 1716, wrote in 1700 on analytical geometry of three dimensions. His works were collected and published in 3 volumes at Paris in 1713. Sarin, Joseph Sarin, born at Cortezan in 1659 and died at Paris on December 29, 1737, was the first to shew how the tangents at the multiple points of curves could be determined by analysis. Degois, Jean-Paul Degois Delmaves, was born at Carcassonne in 1713 and died at Paris on June 2, 1785. He published in 1740 a work on analytical geometry in which he applied it, without the aid of the differential calculus, to find the tangents, asymptotes, and various singular points of an algebraical curve, and he further shewed how singular points and isolated loops were affected by conical projection. He gave the proof of Descartes' rule of signs, which is to be found in most modern works. It is not clear whether Descartes ever proved it strictly, and Newton seems to have regarded it as obvious. Kramer, Gabriel Kramer, born at Geneva in 1704 and died at Bagnols in 1752, was professor at Geneva. The work by which he is best known is his treatise on algebraical curves, published in 1750, which, as far as it goes, is fairly complete. It contains the earliest demonstration that a curve of the nth degree is in general determined if 1/2 n times n plus 3 points on it be given. This work is still sometimes read. Besides this, he edited the works of the 2 elder Bernoullis, and wrote on the physical cause of the spheroidal shapes of the planets and the motion of their apses, 1730, and on Newton's treatment of cubic curves, 1746. Riccati, Jacopo Francesco Count Riccati, born at Venice on May 28, 1676, and died at Treves on April 15, 1754, did a great deal to disseminate a knowledge of the Newtonian philosophy in Italy. Besides the equation known by his name, certain cases of which he succeeded in integrating, he discussed the question of the possibility of lowering the order of a given differential equation. His works were published at Treves in 4 volumes in 1758. He had 2 sons who wrote on several minor points connected with the integral calculus and differential equations, and applied the calculus to several mechanical questions. These were Vincenzo, who was born in 1707 and died in 1775, and Giordano, who was born in 1709 and died in 1790. Fagnano. Giulio Carlo Count Fagnano and Marquise de Tosci, born at Sinigaglia on December 6, 1682, and died on September 26, 1766, may be said to have been the first writer who directed attention to the theory of elliptic functions. Failing to rectify the ellipse or hyperbola, Fagnano attempted to determine arcs whose difference should be rectifiable. He also pointed out the remarkable analogy existing between the integrals which represent the arc of a circle and the arc of a lemniscate. Finally, he proved the formula pi equals 2 times I times the log of 1 minus I divided by 1 plus I, where I stands for the square root of minus 1. His works were collected and published in 2 volumes in Persero in 1750. It was inevitable that some mathematicians should object to methods of analysis founded on the infinitesimal calculus. The most prominent of these were Viviani, de la Hire, and Rolle. Chronologically they come here, but they flourished half a century after the date to which their writings properly belong. Viviani. Vincenzo Viviani, a pupil of Galileo and Torricelli, born at Florence on April 5, 1622, and died there on September 22, 1703, brought out in 1659 a restoration of the lost book of Apollonius on conic sections, and in 1701 a restoration of the work of Aristeas. He explained in 1677 how an angle could be trisected by the aid of an equilateral hyperbola or the conchoid. In 1692 he proposed the problem to construct 4 windows in a hemispherical vault so that the remainder of the surface can be accurately determined, a celebrated problem of which analytical solutions were given by Wallis, Leibniz, David Gregory, and James Bernoulli. De la Hire. Philippe de la Hire or La Hire, born in Paris on March 18, 1640, and died there on April 21, 1719, wrote on graphical methods 1673, on the conic sections 1685, a treatise on epicycloids 1694, one on roulettes 1702, and lastly another on conchoids 1708. His works on conic sections and epicycloids were founded on the teaching of Desargues, whose favourite pupil he was. He also translated the essay of Moschopoulos on magic squares, and collected many of the theorems on them which were previously known. This was published in 1705. Rolle. Michel Rolle, born at Ambert on April 21, 1652, and died in Paris on November 8, 1719, wrote an algebra in 1689 which contains the theorem on the position of roots of an equation which is known by his name. He published in 1696 a treatise on the solution of equations, whether determinate or indeterminate, and he produced several other minor works. He taught that differential calculus was nothing but a collection of ingenious fallacies. So far, no one of the school of Leibniz and the 2 elder Bernoullis had shewn any exceptional ability, but by the action of a number of second-rate writers, the methods and language of analytical geometry and the differential calculus had become well known by about 1740. The close of this school is marked by the appearance of Clairaut, D'Alembert, and Daniel Bernoulli. Their lives overlap the period considered in the next chapter, but though it is difficult to draw a sharp dividing line which shall separate by a definite date the mathematicians there considered from those whose writings are discussed in this chapter, I think that on the whole the works of these 3 writers are best treated here. Clairaut. Alexis Claude Clairaut was born at Paris on May 13, 1713, and died there on May 17, 1765. He belongs to the small group of children who, though of exceptional precocity, survive and maintain their powers when grown up. As early as the age of 12 he wrote a memoir on 4 geometrical curves, but his first important work was a treatise on tortuous curves, published when he was 18, a work which first procured for him immediate admission to the French Academy. In 1731 he gave a demonstration of the fact noted by Newton that all curves of the third order were projections of one of 5 parabolas. In 1741 Clairaut went on a scientific expedition to measure the length of a meridian degree on the earth's surface, and on his return in 1743 he published his Théorie de la figure de la Terre. This is founded on a paper by Maclaurin, where it has been shewn that a mass of homogeneous fluid set in rotation about a line through its center of mass would, under the mutual attraction of its particles, take the form of a spheroid. This work of Clairaut treated of heterogeneous spheroids and contains the proof of his formula for the accelerating effect of gravity in a place of latitude L, namely G equals big G multiplied by 1 plus 5/2 m minus epsilon multiplied by sine squared L, where G is the value of equatorial gravity, m the ratio of the centrifugal force to gravity at the equator, and epsilon the epicity of a meridian section of the Earth. In 1849 Professor Stokes shewed that the same result was true whatever was the interior construction or density of the Earth, provided the surface was a spheroid of equilibrium of small ellipticity. Impressed by the power of geometry as shewn in the writing of Newton and Maclaurin, Clairaut abandoned analysis, and his next work, the Théorie de la Lune, published in 1752, is strictly Newtonian in character. This contains the explanation of the motion of the apse, which had previously puzzled astronomers, and which Clairaut had at first deemed so inexplicable that he was on the point of publishing a new hypothesis as to the law of attraction, when it occurred to him to carry the approximation to the third order, and he thereupon found that the result was in accordance with observations. This was followed in 1754 by some lunar tables. Clairaut subsequently wrote various papers on the orbit of the moon, and on the motion of the comets as affected by the perturbation of the planets, particularly on the path of Halley's comet. His growing popularity in society hindered his scientific work. Engagé, says Bossuet, à des soupers à des vieilles entraînés par un goût vif pour les femmes, voulant aller plaisir à ses travaux ordinaires, et perdre pour la santé enfin via l'âge de 52 ans. D'Alembert. Jean de Rond d'Alembert was born at Paris on November 16, 1717, and died there on October 29, 1713. He was the illegitimate child of the Chevalier d'Estouches. Being abandoned by his mother on the steps of the little church of Saint-Jean-Laurent, which then nestled under the great porch of Notre Dame, he was taken to the parish commissary, who, following the usual practice in such cases, gave him the Christian name of Jean Laurent. I do not know by what title he subsequently assumed the right to prefix de to his name. He was boarded out by the parish, with the wife of a glazier in a small way of business, who lived near the cathedral, and here he seems to have found a real home, though a very humble one. His father appears to have looked after him and paid for his going to a school where he obtained a fair mathematical education. An essay written in 1738 on the integral calculus, and another in 1740 on ducks and drakes, or ricochets, attracted some attention, and in the same year he was elected a member of the French Academy. This was probably due to the influence of his father. It is to his credit that he absolutely refused to leave his adopted mother, with whom he continued to live until her death in 1757. It cannot be said that she sympathized with his success, for, at the height of his fame, she remonstrated with him for wasting his talents on such work. Vous ne serez aimé qu'un philosophe, said she. Et qu'est-ce qu'un philosophe? C'est un fou qui se tourmente pendant sa vie, pour qu'on parle de lui lorsqu'il ne sera plus. Nearly all his mathematical works were produced within the years 1743 to 1754. The first of these was his Traité de dynamique, published in 1743, in which he enunciates the principle known by his name, namely that the internal forces of inertia, i.e. the forces which resist acceleration, must be equal and opposite to the forces which produce the acceleration. This is a particular case of Newton's second reading of his third law of motion, but the full consequence of it had not been realized previously. The application of this principle enables us to obtain the differential equations of motion of any rigid system. In 1744, D'Alembert published his Traité de l'équilibre et du mouvement des fluides, in which he applies his principle to fluids. This led to partial differential equations which he was then unable to solve. In 1745 he developed that part of the subject which dealt with the motion of air in his Théorie générale des vents, and this again led him to partial differential equations. A second edition of this in 1746 was dedicated to Frederick the Great of Prussia, and procured an invitation to Berlin and the offer of a pension. He declined the former, but subsequently, after some pressing, pocketed his pride and the latter. In 1747 he applied the differential calculus to the problem of a vibrating string, and again arrived at a partial differential equation. His analysis had 3 times brought him to an equation of the form the second derivative of u with respect to t equals the second derivative of u with respect to x. And he now succeeded in shewing that it was satisfied by u equals phi of x plus t plus psi of x minus t, where phi and psi are arbitrary functions. It may be interesting to give his solution, which was published in the Transactions of the Berlin Academy for 1747. He begins by saying that if the partial derivative of u with respect to x be denoted by p and the partial derivative of u with respect to t by q, then du equals p dx plus q dt. But by the given equation, the partial derivative of q with respect to t equals the partial derivative of p with respect to x, and therefore p dt plus q dx is also an exact differential denoted by dv. Therefore, dv equals p dt plus q dx. Hence du plus dv equals p dx plus q dt plus p dt plus q dx equals p plus q multiplied by dx plus dt. And du minus dv equals p dx plus q dt minus the quantity p dt plus q dx equals the quantity p minus q multiplied by the quantity dx minus dt. Thus u plus v must be a function of x plus t, and u minus v must be a function of x minus t. We may therefore put u plus v equals 2 times phi of x plus t, and u minus v equals 2 psi of x minus t. Hence u equals phi of x plus t plus psi of x minus t. D'Alembert added that the conditions of the physical problem of a vibrating string demand that when x equals 0, u should vanish for all values of t. Hence, identically, phi of t plus psi of negative t equals 0. Assuming that both functions can be expanded in integral powers of t, this requires that they should contain only odd powers. Hence, psi of negative t equals negative phi of t equals phi of negative t. Therefore, u equals phi of x plus t plus phi of x minus t. Euler now took the matter up and shewed that the equation of the form of the string was the second derivative of u with respect to t equals a squared multiplied by the second derivative of u with respect to x, and that the general integral was u equals phi of x minus at plus psi of x plus at, where phi and psi are arbitrary functions. The chief remaining contributions of D'Alembert to mathematics were on physical astronomy, especially on the precession of the equinoxes and on variations of the obliquity of the ecliptic. These were collected on his Système des Mondes, published in 3 volumes in 1754. During the latter part of his life he was mainly occupied with the great French encyclopaedia. For this he wrote the introduction, and numerous philosophical and mathematical articles. The best are those on geometry and on probabilities. His style is brilliant but not polished, and faithfully reflects his character, which was bold, honest, and frank. He defended a severe criticism which he had offered on some mediocre work by the remark, J'aime mieux être incivil qu'ennuyé. And with his dislike of sycophants and bores, it is not surprising that during his life he had more enemies than friends. End of section 28. Recording by Paul King, Oakville, Ontario. pjk.scripts.mit.edu/pkj. Chapter 17, Part 3 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading is by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics by Rouse. Chapter 18, Leibniz and the mathematicians of the first half of the 18th century. Daniel Bernoulli. Daniel Bernoulli, whose name I mentioned above, and who was by far the ablest of the younger Bernoullis, was a contemporary and intimate friend of Euler, whose works are mentioned in the next chapter. Daniel Bernoulli was born on February 9, 1700, and died at Bâle, where he was professor of natural philosophy, on March 17, 1782. He went to St. Petersburg in 1724 as professor of mathematics, but the roughness of the social life was distasteful to him, and he was not sorry when a temporary illness in 1733 allowed him to plead his health as an excuse for leaving. He then returned to Bâle, where he held successively chairs of medicine, metaphysics, and natural philosophy there. His earliest mathematical work was on the Excursiones, published in 1724. These contain a theory of the oscillations of rigid bodies, and a solution to the differential equations proposed by Riccati. 2 years later, he pointed out for the first time the frequent desirability of resolving a compound motion into motions of translation and motions of rotation. His chief work is his Hydrodynamique, published in 1738. It resembles Lagrange's Mécanique analytique in being arranged so that all the results are consequences of a single principle, namely in this case the conservation of energy. This was followed by a memoir on the theory of the tides, to which, conjointly with memoirs by Euler and Maclaurin, a prize was awarded by the French Academy. These 3 memoirs contain all that was done on the subject between publication of Newton's Principia and the investigations of Laplace. Bernoulli also wrote a large number of papers on various mechanical questions, especially on problems connected with vibrating strings, and the solutions given by Taylor and D'Alembert. He is the earliest writer who attempted to formulate a kinetic theory of gases, and he applied the idea to explain the law associated with the names of Boyle and Mariotte. The English mathematicians of the 18th century. I have reserved a notice of the English mathematicians who succeeded Newton in order that the members of the English school may all be treated together. It was almost a matter of course that the English should at least at first have adopted the notation of Newton in the infinitesimal calculus in preference to that of Leibniz, and the English school would consequently in any case have developed on somewhat different lines to that of the continent, where a knowledge of the infinitesimal calculus was derived solely from Leibniz and the Bernoullis. But this separation into two distinct schools became very marked owing to the action of Leibniz and John Bernoulli, which was naturally resented by Newton's friends, and so for 40 or 50 years, to the mutual disadvantage of both sides, the quarrel raged. The leading members of the English school were Coates, de Moivre, Ditton, David Gregory, Halley, Maclaurin, Simpson, and Taylor. I may, however, again remind my readers that as we approach the modern times, the number of capable mathematicians in Britain, France, Germany, and Italy becomes very considerable, but that in a popular sketch like this book, it is only the leading men who I propose to mention. To David Gregory, Halley, and Ditton I need to devote but a few words. David Gregory. David Gregory, the nephew of James Gregory mentioned above in page 315, born at Aberdeen on June 24, 1661 and died at Maidenhead on October 10, 1708, was appointed professor at Edinburgh in 1684 and in 1691 was, on Newton's recommendation, elected Savilian professor at Oxford. His chief works are one on geometry, issued in 1684, one on optics, published in 1695, which contains the earliest suggestion of the possibility of making an achromatic combinations of lenses, and one on the Newtonian geometry, physics, and astronomy, issued in 1702. Halley. Edmund Halley, born in London in 1656 and died at Greenwich in 1742, was educated at St. Paul's School, London, and Queen's College, Oxford in 1703, succeeded Wallace as Savilian professor, and subsequently in 1720 was appointed Astronomer Royal in succession to Flamsteed, whose Historia Caelestis Britannica he edited in 1712, first and imperfect edition. Halley's name will be recollected for the generous manner in which he secured the immediate publication of Newton's Principia in 1687. Most of his original work was on astronomy and allied subjects and lies outside the limits of this book. It may be, however, said that the work is of excellent quality, and both Lalande and Meran speak of it in the highest terms. Halley conjecturally restored the eighth and lost book of the Conics of Apollonius, and in 1710 brought out a magnificent edition of the whole work. He also edited the works of Serenus and those of Menelaus, and some of the minor works of Apollonius. He was in his turn succeeded at Greenwich as an Astronomer Royal by Bradley. Ditton. Humphrey Ditton, born at Salisbury on May 29, 1675, and died in London in 1715 at Christ's Hospital, where he was mathematical master. He does not seem to have paid much attention to mathematics until he came to London about 1705, and his early death was a distinct loss to English science. He published in 1706 a textbook on fluxions. This and another similar work by William Jones, which was issued in 1711, occupied in England much the same place as L'Hopital's treatise did in France. In 1709, Ditton issued an algebra, and in 1712 a treatise on perspective. He also wrote numerous papers on the philosophical transactions. He was the earliest writer to attempt to explain the phenomenon of capillary on mathematical principles, and he invented a method of finding the longitude which has been since used on various occasions. Taylor. Brooke Taylor, born at Edmonton on August 18, 1685, and died in London on December 29, 1731, was educated at St. John's College, Cambridge, and was among the most enthusiastic of Newton's admirers. From the year 1712 onwards, he wrote numerous papers on philosophical transactions, in which, among other things, he discussed the motion of projectiles, the centre of oscillation, and the forms of liquids raised by capillarity. In 1719 he resigned the secretaryship of the Royal Society and abandoned the study of mathematics. His earliest work, that by which he is generally known, is his Methodus Incrementorum Directa et Inversa, published in London in 1715. This contains a proof of the well-known theorem f of x plus h equals f of x plus h f primed of x plus h squared over 2 factorial multiplied by f double primed of x plus and so on, by which any function of a single variable can be expanded in powers of it. He does not consider the convergency of the series, and the proof, which involves numerous assumptions, is not worth reproducing. The work also includes several theorems on interpolation. Taylor was the earliest writer to deal with theorems on the change of the independent variable. He was perhaps the first to realize the possibility of a calculus of operation, and just as he denotes the nth differential coefficient of y by y sub n, so he uses y sub negative 1 to represent the integral of y. Lastly, he is usually recognized as the creator of the theory of finite differences. The applications of the calculus to various questions given in the Methodists have hardly received that attention they deserve. The most important of them is the theory of the transverse vibration of strings, a problem which had baffled previous investigators. In this investigation, Taylor shows that the number of half vibrations executed in a second is pi multiplied by the square root of the quantity dp divided by ln, where L is the length of the string, n is its weight, p is the weight which stretches it, and d is the length of a second's pendulum. This is correct, but in arriving at it he assumes that every point on the string will pass through its position of equilibrium at the same instant, a restriction which de la Berne subsequently shewed to be unnecessary. Taylor also found the form which the string assumes at any instant. This work also contains the earliest determination of the differential equation of the path of a ray of light when traversing a heterogeneous medium, and assuming that the density of the air depends only on its distance from the Earth's surface, Taylor obtained by means of quadratures the approximate form of the curve. The form of the catenary and the determination of the centers of oscillation and percussion are also discussed. A treatise on perspective, published in 1719, contains the earliest general enunciation of the principle of vanishing points. Though the idea of vanishing points for horizontal and parallel lines in a picture hung in a vertical plane had been enunciated by Guido Ubaldi in his Perspective Libri, Pisa, 1600. Coates. Roger Coates was born near Leicester on July 10, 1682, and died at Cambridge on June 5, 1716. He was educated at Trinity College, Cambridge, of which society he was a fellow, and in 1706 was elected to the newly created Plumian Chair of Astronomy in the University of Cambridge. From 1709 to 1713 his time was mainly occupied in editing the second edition of the Principia. The remark of Newton that if only Coates had lived we should have learnt something indicates the opinion of his abilities held by most of his contemporaries. Coates's writings were collected and published in 1722 under the titles Harmonia Mensurarum and Opera Miscellanea. His lectures on hydrostatics were published in 1738. A large part of the Harmonia Mensuratum was given up to the decomposition and integration of rational algebraical expressions. That part which deals with the theory of partial fractions was left unfinished, but was completed by De Moivre. Coates's theorem in trigonometry, which depends on forming the quadratic factors of x to the power n minus 1, is well known. The proposition that if from a fixed point O a line be drawn cutting a curve in Q1, Q2, and so on to Qn, and a point P be taken on the line so that the reciprocal of OP is the arithmetic mean of the reciprocals of OQ1, OQ2, OQ3, and so on all the way to OQn, then the locus of P will be a straight line, is also due to Coates. The title of the book was derived from the latter theorem. The Opera Miscellanea contains a paper on the method for determining the most probable result from a number of observations. This was the earliest attempt to frame a theory of errors. It also contains essays on Newton's Methodus Differentialis, the construction of tables by the method of differences, on the descent of a body under gravity, on the cycloidal pendulum, and on projectiles. Demoivre. Abraham Demoivre, more correctly written Demoivre in 2 words, was born at Vitry in May 26, 1667, and died in London on November 27, 1754. His parents came to England when he was a boy, and his education and friends were alike English. His interest in the higher mathematics is said to have originated in his coming by chance across a copy of Newton's Principia. From the Eloge on him delivered in 1754 before the French Academy, it would seem that as a young fellow his work as a teacher of mathematics had led him to the house of the Earl of Devonshire at the instant when Newton, who had asked permission to present a copy of his work to the Earl, was coming up. Taking up the book, and charmed by the far-reaching conclusions and the apparent simplicity of the reasoning, Demoivre thought nothing would be easier than to master the subject, but to his surprise found that to follow the argument overtaxed his powers. He however bought a copy, and as he had but little leisure, he tore out the pages in order to carry 1 or 2 of them loose in his pocket, so that he could study them in the intervals of his work as a teacher. Subsequently he joined the Royal Society, and he became intimately connected with Newton, Halley, and other mathematicians of the English school. The manner of his death has a curious interest for psychologists. Shortly before it, he declared that it was necessary for him to sleep some 10 minutes or a quarter of an hour longer each day than the preceding one. The day after he had thus reached a total of something over 23 hours, he slept up to the limit of 24 hours and then died in his sleep. He is best known for having, together with Lambert, created that part of trigonometry which deals with imaginary quantities. 2 theorems on this part of the subject are still connected with his name, namely that which asserts that sine nx plus I cos nx is one of the values of the quantity sine x plus I cos x all to the power n, and that which gives the various quadratic factors of x to the power 2n minus 2 times px to the power n plus 1. His chief works, other than numerous papers in the Philosophical Transactions, were the Doctrine of Chances, published in 1718, and the Miscellanea Analytica, published in 1730. In the former, the theory of recurring series was first given, and the theory of partial fractions, which Coates's premature death had left unfinished, was completed, while the rule for finding the probability of a compound event was enunciated. The latter, besides the trigonometrical propositions mentioned above, contain some theorems in astronomy, but they are treated as problems in analysis. Maclaurin. Colin Maclaurin, who was born in Kilmodden in Argyllshire in February 1698 and died at York on June 14, 1746, was educated at the University of Glasgow. In 1717 he was elected, at the early age of 19, professor of mathematics at Aberdeen, and in 1725 he was appointed the deputy of the mathematical professor at Edinburgh, and ultimately succeeded him. There was some difficulty in securing a stipend for a deputy, and Newton privately wrote offering to bear the cost so as to enable the university to secure the services of Maclaurin. Maclaurin took an active part in opposing the advance of the Young Pretender in 1745. On the approach of the Highlanders he fled to York, but the exposure in the trenches at Edinburgh and the privations he endured in his escape proved fatal to him. His chief works are Geometrica Organica, London 1719, his treatise on fluxions, Edinburgh 1742, his Algebra, London 1748, and his account of Newton's discoveries, London 1748. The Geometrica Organica is on the extension of a theorem given by Newton. Newton had shewn that if 2 angles bounded by straight lines turned round their respective summits so that the point of intersection of 2 of these lines moves along a straight line, the other point of intersection will describe a conic, and if the first point move along a conic, the second will describe a quartic. Maclaurin gave an analytical discussion on the general theorem and shewed by how this method various curves could be practically traced. This work contains an elaborate discussion on curves and their pedals, a branch of geometry which he had created in two papers published in the Philosophical Transactions for 1718 and 1719. In the following year, 1720, Maclaurin issued a supplement which is practically the same as his De Linearum Geometricarum Proprietatibus. It is divided into three sections and an appendix. The first section contains a proof of Coates' theorem as alluded to, and also the analogous theorem discovered by himself that if a straight line OP1P2 is drawn through a fixed point O, cut a curve of the nth degree in n points p1, p2, and so on, and if the tangents at p1, p2 cut in a fixed line OX in points a1, a2, and so on, then the sum of the reciprocals of the distances OA1, OA2, and so forth is constant for all positions of the line OP1, P2, and so on. These two theorems are generalizations of those given by Newton on diameters and asymptotes. Either is deducible from the other. In the second section, these theorems are applied to conics. Most of these harmonic properties connected with an inscribed quadrilateral are determined, and in particular the theorem on an inscribed hexagon, which is known by the name of Pascal, is deduced. Pascal's essay was not published until 1779, and the earliest printed enunciation of his theorem was that given by Maclaurin. In the third section, these theorems are applied to cubic curves. Amongst other propositions, he shews that if a quadrilateral be inscribed in a cubic, and if the points of intersection of the opposite sides also lie on the curve, then the tangents to the cubic at any two opposite angles of the quadrilateral will meet on the curve. The appendix contains some general theorems. One of these, which includes Pascal's as a particular case, is that if a polygon be deformed so that while each of its sides passes through a fixed point, its angles save one describe respectively curves of the mth, nth, pth, and so forth degrees, then shall the remaining angle describe a curve of the degree 2 MNP. But if the given points be collinear, the resulting curve will be only of the degree MNP. This essay was reprinted with additions on the Philosophical Transactions for 1735. The treatise of fluxions, published in 1742, was the first logical and systematic exposition of the method of fluxions. The cause of its publication was an attack by Berkeley on the principles of the infinitesimal calculus. In it, Article 751, page 610, Maclaurin gave a proof of the theorem that f of x equals f of 0 plus xf prime of 0 plus x squared over 2 factorial f double prime of 0 plus so on and so forth. This was obtained in the manner given in many modern textbooks by assuming that f of x can be expanded in a form like f of x equals a naught plus a1x plus a2x squared plus and so on and so on. Then on differentiating and putting x equals 0 in the successive results, the values of a0, a1, and so on are obtained. But he did not investigate the convergency of the series. The result had been previously given in 1730 by James Stirling in his Methodes Differentiales, and of course is at once deducible from Taylor's theorem, on which the proofs by Stirling and Maclaurin are admittedly founded. Maclaurin also here enunciated, Article 350, page 289, the important theorem that if phi x be positive and decrease as x increases from x equals a to x equals infinity, then the series phi of a plus phi of a plus 1 plus phi of a plus 2 and so on is convergent or divergent, as the integral going from a to infinity of phi of x dx is finite or infinite. He also gives the correct theory of maxima and minima, and rules for finding and discriminating multiple points. This treatise is, however, especially valuable for the solutions it contains of numerous problems in geometry, statics, the theory of attractions, and astronomy. To solve these, he reverted to classical methods, and so powerful did these processes seem, when used by him, that Clairaut, after reading the work, abandoned analysis, and attacked the problem of the figure of the earth again by pure geometry. At a later time this part of the book was described by Lagrange as the chef d'œuvre de géométrie qu'on peut comparer à tout ce qu'Archimède nous a laissé de plus beau et de plus ingénieux. Maclaurin also determined the attraction of a homogeneous ellipsoid at an internal point and gave some theorems on its attraction at an external point. In effecting this he introduced the conception of level surfaces, i.e. surfaces at every point of which the resultant attraction is perpendicular to the surface. No further advances in the theory of attractions was made until Lagrange in 1773 introduced the idea of the potential, see below. Maclaurin also shewed that a spheroid was a possible form of equilibrium of a mass of homogeneous liquid rotating about an axis passing through its centre of mass. Finally, he discussed the tides. This part had been previously published in 1740 and had received a prize from the French Academy. Among Maclaurin's minor works is his Algebra, published in 1748 and founded on Newton's Universal Arithmetic. It contains the results of some early papers of Maclaurin, notably of two, written in 1726 and 1729, on the number of imaginary roots of an equation, suggested by Newton's theorem, see above, and of one written in 1729 containing the well-known rule for finding equal roots by means of the derived equation. To this a treatise entitled De Linearum Geometricarum Proprietatibus Generalibus was added as an appendix. Besides the paper of 1720 above alluded to, it contains some additional and elegant theorems. Maclaurin also produced in 1728 an exposition of the Newtonian philosophy, in which is incorporated in the posthumous work printed in 1748. Almost the last paper he wrote was one printed in the Philosophical Transactions in 1743, in which he discussed from a mathematical point of view the form of a bee's cell. Maclaurin was succeeded in his chair at Edinburgh by pupil Matthew Stewart, born at Rothesay in 1717 and died in Edinburgh on January 23, 1785, a mathematician of considerable power, to whom I allude in passing for his theorems on the problem of three bodies and for his discussion treated by transversals and involution of the properties of the circle and straight line. Maclaurin was one of the most able mathematicians of the 18th century, but his influence on the progress of British mathematics was on the whole unfortunate. By himself abandoning the use of both analysis and of the infinitesimal calculus, he induced Newton's countrymen to confine themselves to Newton's methods, and I remarked before it was not until about 1820, when the differential calculus was introduced into the Cambridge curriculum, that English mathematicians made any general use of the more powerful methods of modern analysis. Simpson. The last member of the English school whom I need mention here is Thomas Simpson, who was born in Leicestershire on August 20th, 1710, and died on May 14th, 1761. His father was a weaver, and he owed his education to his own efforts. His mathematical interests were first aroused by the solar eclipse which took place in 1724, and with the aid of a fortune-telling peddler he mastered the Cocker's arithmetic and the elements of algebra. He then gave up his weaving and became an usher at a school, and by constant and laborious efforts improved his mathematical education, so that by 1735 he was able to solve several questions involving the infinitesimal calculus, which had been recently proposed. He next moved to London and in 1743 was appointed professor of mathematics at Woolwich, a post which he continued to occupy till his death. The works published by Simpson prove him to have been a man of extraordinary natural genius and extreme industry. The most important of them are his Fluxions, 1737 and 1750, with numerous applications to physics and astronomy, his Laws of Chance and his Essays, 1740, and his Theory of Annuities and Reversions, a branch of mathematics that is due to James Dodson, 1597 to 1657, who was a master at Christ's Hospital, London, with Tables of the Value of Lives, 1742, his Dissertations, 1743, in which the figure of the earth, the force of attraction at the surface of a nearly spherical body, the theory of the tides, and the law of astronomical refraction are discussed. His Algebra, 1745, his Geometry, 1747, his Trigonometry, 1748, in which he introduced the current abbreviations for the trigonometrical functions, his Select Exercises, 1752, containing the solutions of numerous problems and a theory of gunnery, and lastly his Miscellaneous Tracts, 1754. The last consists of 8 memoirs, and these contain his best known investigations. The first 3 papers are on various problems in astronomy, the fourth is on the theory of mean observations, the fifth and sixth on problems in fluxions and algebra, the seventh contain a general solution of the isoperimetrical problem, the eighth contains a discussion of the third and ninth sections of the Principia and their application to the lunar orbit. In this last memoir, Simpson attained a differential equation for the motion of the apse of the lunar orbit, similar to that arrived at by Clairaut, but instead of solving it by successive approximations, he deduced a general solution by indeterminate coefficients. The result agrees with that given by Clairaut. Simpson first solved this problem in 1747, 2 years later than the publication of Clairaut's memoir, but the solution was discovered independently of Clairaut's researches, of which Simpson first heard in 1748. End of section 29. Recording by Paul King, Oakville, Ontario, pjk.scripts.mit.edu/pkj. Chapter 18, Part 1 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading is by Paul King, pjk.scripts.mit.edu/pkj. A Short Account of the History of Mathematics by W. W. Rouse. Chapter 18. Lagrange, Laplace, and their contemporaries, circa 1740 to 1830. The last chapter contains the history of 2 separate schools, the continental and the British. In the early years of the 18th century, the English school appeared vigorous and fruitful, but decadence rapidly set in, and after the deaths of Maclaurin and Simpson, no British mathematician appeared who is at all comparable to the continental mathematicians of the latter half of the 18th century. This fact is partly explicable by the isolation of the school, partly by its tendency to rely too exclusively on geometrical and fluxional methods. Some attention was, however, given to practical science, but, except for a few remarks on English physicists, I do not think it necessary to discuss English mathematicians further until about 1820, when analytical methods again come into vogue. On the continent, under the influence of John Bernoulli, the calculus had become an instrument of great analytical power expressed in an admirable notation, and for practical applications it is impossible to overestimate the value of a good notation. The subject of mechanics remained however in much the condition in which Newton had left it, until D'Alembert, in putting Newton's results into the language of the differential calculus, did something to extend it. Universal gravitation as enunciated in the Principia was accepted as an established fact, but the geometrical methods adopted in proving it were difficult to follow or to use in analogous problems. Maclaurin, Simpson, and Clairaut may be regarded as the last mathematicians of distinction who employed them. Lastly, the Newtonian theory of light was generally received as correct. The leading mathematicians of the era of which we are now entering are Euler, Lagrange, Laplace, and Legendre. Briefly, we may say that Euler extended, summed up, and completed the work of his predecessors, while Lagrange, with almost unrivalled skill, developed the infinitesimal calculus and theoretical mechanics into the form in which we now know them. At the same time, Laplace made some additions to the infinitesimal calculus and applied that calculus to the theory of universal gravitation. He also created a calculus of probabilities. Legendre invented spherical harmonic analysis and elliptic integrals and added to the theory of numbers. The works of these writers are still standard authorities and are hardly yet the subject matter of history. I shall therefore content myself with a mere sketch of their discoveries, referring anyone who wishes to know more to the works themselves. Lagrange, Laplace, and Legendre created a French school of mathematics, of which the younger members are divided into two groups, including Poisson and Fourier, began to apply the mathematical analysis to physics, and the other, including Monge, Carnot, and Poncelet, created modern geometry. Strictly speaking, some of the great mathematicians of recent times, such as Gauss and Abel, were contemporaries of the mathematicians last named, but except for this remark, I think it convenient to defer any consideration of them to the next chapter. The development of analysis and mathematics. Euler. Leonhard Euler was born in Bâle on April 15th, 1707, and died at St. Petersburg on September 7th, 1783. He was a son of a Lutheran minister who had settled at Bâle and was educated in his native town under the direction of John Bernoulli, with whose sons Daniel and Nicholas he formed a lifelong friendship. When in 1725 the younger Bernoullis went to Russia on the invitation of the Empress, they procured a place there for Euler, which in 1733 he exchanged for the chair of mathematics then vacated by Daniel Bernoulli. The severity of the climate affected his eyesight, and in 1735 he lost the use of one eye completely. In 1741 he moved to Berlin at the request, or rather command, of Frederick the Great. Here he stayed till 1766, when he returned to Russia, and was succeeded at Berlin by Lagrange. Within 2 or 3 years of his going back to St. Petersburg he became blind, but in spite of this, and although his house together with many of his papers were burnt in 1771, he recast and improved most of his earlier works. He died of apoplexy in 1783. He was married twice. I think we may sum up Euler's work by saying that he created analysis and revised almost all the branches of pure mathematics which were then known, filling up the details, adding proofs, and arranging the whole in consistent form. Such work is very important, and it is fortunate for science when it falls into the hands as competent as those of Euler. Euler wrote an immense number of memoirs on all kinds of mathematical subjects. His chief work, in which many of the results of earlier memoirs are embodied, are as follows. In the first place, he wrote in 1748 in his Introductio in Analysem Infinitorum, which was intended to serve as an introduction to pure analytical mechanics. This is divided into 2 parts. The first part of the Analysis Infinitorum contains the bulk of the matter which is to be found in the modern textbooks on algebra, theory of equations, and trigonometry. In the algebra, he paid particular attention to the expansion of various functions in series and to the summation of given series, and pointed out explicitly that an infinite series cannot be safely employed unless it is convergent. In the trigonometry, much of which is founded on F. C. Mayer's Arithmetic of Sines, which has been published in 1727, Euler developed the idea of John Bernoulli that the subject was a branch of analysis and not a mere appendage of astronomy or geometry. He also introduced, contemporaneously with Simpson, the current abbreviations for the trigonometrical functions, and shewed that the trigonometrical and exponential functions were connected by the relation cosine theta plus I sine theta equals e to the power of I times theta. Here too we meet the symbol e, used to denote the base of the Napierian logarithms, namely the incommensurable number 2.71828, and the symbol pi, used to denote the incommensurable number 3.14159. The use of a single symbol to denote the number 2.71828 seems to be due to Coates, who denoted it by m. Newton was, as far as I know, the first to employ the literal exponential notation, and Euler, using the form a to the z, has taken a as the base of any system of logarithms. It is probable that the choice of e for a particular base was determined by its being the vowel consecutive to a. The use of a single symbol to denote the number 3.14159 appears to have been introduced by John Bernoulli, who represented it by c. Euler in 1734 denoted it by p, and in a letter of 1736 in which he enunciated the theorem that the sum of the squares of the reciprocals of the natural numbers is 1 over 6 times pi squared, he used the letter c. Christian Goldbach in 1742 used the Greek letter pi, and after the publication of Euler's analysis the symbol pi was generally employed. The numbers e and pi would enter into the mathematical analysis from whatever side the subject was approached. The latter represents, among other things, the ratio of the circumference of a circle to the diameter, but it is a mere accident that it is taken for its definition. De Morgan, in the Budget of Paradoxes, tells an anecdote which illustrates how little the usual definition suggests its real use. He was explaining to an actuary what was the chance that at the end of a given time a certain proportion of some group of people would be alive, and quoted the actuarial formula involving pi, which in answer to a question he explained stood for the ratio of the circumference of a circle to its diameter. His acquaintance, who so far listened to the explanation with interest, interrupted him and explained, "My dear friend, that must be a delusion. What can a circle have to do with the number of people alive at the end of a given time?" The second part of the Analysis Infinitorum is on analytical geometry. Euler commenced this part by dividing curves into algebraical and transcendental, and established a variety of propositions which are true for all algebraical curves. He then applied these to the general equations of the second degree in 2 dimensions, shewed that it represents the various conic sections, and deduced most of their properties from the general equation. He also considered the classification of cubic, quartic, and other algebraical curves. He next discussed the question as to what surfaces are represented by the general equation of the second degree in 3 dimensions, and how they may be discriminated one from the other. Some of these surfaces had not been previously investigated. In the course of this analysis he laid down the rules for the transformation of coordinates in space. Here also we find the earliest attempt to bring the curvature of surfaces within the domain of mathematics, and the first complete discussion of tortuous curves. The Analysis Infinitorum was followed in 1755 by the Institutiones Calculi Differentialis, to which it was intended as an introduction. This was the first textbook on the differential calculus which has any claim to be regarded as complete, and it may be said that most modern treatises on the subject are based on it. At the same time it should be added that the exposition of the principles of the subject is often prolix and obscure, and sometimes not altogether accurate. This series of works was completed by the publication in 3 volumes, in 1768 to 1770, of the Institutiones Calculi Integralis, in which the results of several of Euler's earlier memoirs on the same subject and on differential equations are included. This, like the similar treatise on the differential calculus, summed up what was then known on the subject, but many of the theorems were recast and the proofs improved. The beta and gamma functions were invented by Euler and discussed here, but only as illustrations of the methods of reduction and integration. His treatment of elliptical integrals is superficial. It was due to a theorem given by John Landon, a writer who was suggestive rather than powerful, in the Philosophical Transactions for 1755, connecting the arcs of a hyperbola and an ellipse. Euler's works that form this trilogy have gone through numerous subsequent editions. The classic problems on isoperimetrical curves, the brachistochrone in a resulting medium, and the theory of geodesics, all of which had been suggested by his master John Bernoulli, had engaged Euler's attention at an early date, and in solving them he was led to the calculus of variations. The general idea of this was laid down in his Curvarum Maximae Minive Proprietate Gaudentium Inventio Nova ac Facilis, published in 1744, but the complete development of the new calculus was first effected by Lagrange in 1759. The method used by Lagrange is described in Euler's integral calculus and is the same as that given in most modern textbooks on the subject. In 1770 Euler published the Analyse zur Algebra in 2 volumes. The first volume treats of determinate algebra. This contains one of the earliest attempts to place the fundamental process on a scientific basis. The same subject had attracted D'Alembert's attention. This work also includes the proof of the binomial theorem for an unrestricted index, which is still known by Euler's name. The proof is founded on the principle of the permanence of equivalent forms, but Euler made no attempt to investigate the convergency of the series. That he should have omitted this essential step is the more curious, as he had himself recognized the necessity of considering the convergency of the infinite series. The second volume treats of the indeterminate or Diophantine algebra. This contains a solution of some of the problems proposed by Fermat, which had hitherto remained unsolved. A French translation of the algebra, with numerous and valuable additions by Lagrange, was brought out in 1794, and a treatise on arithmetic by Euler was appended to it. These 4 works comprise most of what Euler produced in pure mathematics. He also wrote numerous memoirs on nearly all subjects of applied mathematics and mathematical physics then studied. The chief results in them are as follows. In the mechanics of a grid system he determined the general equation of a motion of a body about a fixed point, which are ordinarily written of the form a multiplied by d omega 1 by dt minus in brackets b minus c close bracket times omega 2 times omega 3 equals L. And he gave the general equation of the motion of a free body, which are usually presented in the form d by dt times mu minus mv theta 3 plus mw theta 2 equals x, and dh1 prime by dt equals h2 prime theta 3 plus h3 prime theta 2 equals L. He also defended and elaborated the theory of least action, which had been propounded by Maupertuis in 1751 in his Essai de cosmologie. In hydrodynamics, Euler established the general equations of motion, which are commonly expressed in the form 1 over rho d rho by dx equals x minus du by dt minus u times du by dx minus v times du by dy minus w times du by dz. At the time of his death he was engaged in writing a treatise on hydromechanics in which the treatment of the subject would have been completely recast. His most important works on astronomy are his Theoria Mortuum Planetarum et Cometarum, published in 1744, his Theoria Motus Lunaris, published in 1753, and his Theoria Motuum Lunae, published in 1772. In these he attacked the problem of three bodies. He supposed the body considered, e.g. the moon, to carry three rectangular axes with it in its motion, the axes moving parallel to themselves, and to these axes all the motions were referred. This method is not convenient, but it was from Euler's results that Mayer constructed the lunar tables, from which his widow in 1770 received £5,000, being the prize offered by the English Parliament, and in recognition of Euler's services a sum of £300 was voted as an honorarium to him. Euler was much interested in optics. In 1746 he discussed the relative merits of the emission and undulatory theories of light. He on the whole preferred the latter. In 1770 to 1771 he published his optical researches in 3 volumes under the title Dioptrica. He also wrote an elementary work on physics and fundamental principles of mathematical philosophy. This originated from an invitation he received when he first went to Berlin to give the lessons on physics to the Princess of Anhalt-Dessau. These lectures were published in 1768 to 1772 in 3 volumes under the title Lettres sur quelques sujets de physique, and for half a century remained a standard treatise on the subject. Of course, Euler's magnificent works were not the only textbooks containing original matter produced at this time. Amongst numerous writers I would specially single out Daniel Bernoulli, Simpson, Lambert, Bézout, Tremblay, and Arbogast as having influenced the development of mathematics. To the first 2 mentioned I have already alluded in the last chapter. End of section 30. Recording by Paul King, Oakville, Ontario, pjk.scripps.mit.edu/pkj. Chapter 18, Part 2 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by Rouse. Chapter 18, Leibniz and the mathematicians of the first half of the 18th century, Part 2. Lambert. Johann Heinrich Lambert was born at Mühlhausen on August 28, 1728, and died at Berlin on September 25, 1777. He was the son of a small tailor, and had to rely on his own efforts for his education. From a clerk in some ironworks, he got a place in a newspaper office, and subsequently, on the recommendation of the editor, he was appointed tutor in a private family which secured him the use of a good library, and sufficient leisure to use it. In 1759 he settled in Augsburg, and in 1733 removed to Berlin, where he was given a small pension, and finally made editor of the Prussian Astronomical Almanac. Lambert's most important work were one on optics, issued in 1759, which suggested to Arago the lines of investigation he subsequently pursued, a treatise on perspective published in 1759, to which in 1768 an appendix giving practical applications was added. and a treatise on comets printed in 1761 containing the well-known expression for the area of a focal sector of a conic in terms of the chord and the bounding radii. Besides these, he communicated numerous papers to the Berlin Academy. Of the most important are his memoir in 1768 on transcendental magnitudes, in which he proved that pi is incommensurable. The proof is given in Legendre's Géométrie and is there extended to pi squared. His paper on trigonometry, read in 1768, in which he developed de Moivre's theorems on the trigonometry of complex variables and introduced the hyperbolic sine and cosine denoted by the symbols sin hx, cos hx. His essay entitled The Analytical Observations, published in 1771, which is the earliest attempt to form the functional equations by expressing the given properties in the language of the differential calculus and then integrating. Lastly, his paper on vis viva, published in 1783, in which for the first time he expressed Newton's second law of motion in the notation of the differential calculus. Of the other mathematicians above mentioned, I here add a few words. Etienne Bezout, born in Namur on March 31st, 1730, and died on September 27th, 1783, besides numerous minor works, wrote a Théorie générale des équations algébriques, published at Paris in 1779, which in particular contained much new and valuable matter on the theory of elimination and symmetrical functions of the roots of an equation. He used as determinants in a paper in the Histoire de l'Académie Royale, 1764, but did not treat of the general theory. Jean Tremblay, born at Geneva in 1749 and died at September 18, 1811, contributed to the development of differential equations, finite differences, and the calculus of probabilities. Louis-François d'Antoine Arbogast, born at Alsace on October 4, 1759, and died at Strasbourg, where he was professor, on April 8, 1803, wrote on series and the derivatives known by his name. He was the first writer to separate the symbols of operation from those of quantity. I do not wish to crowd my pages with an account of those who have not distinctly advanced the subject, but I have mentioned the above writers because their names are still well known. We may however say that the discoveries of Euler and Lagrange in the subjects which they treated were so complete and far-reaching that what their less gifted contemporaries added is not of sufficient importance to require mention in a book of this nature. Lagrange. Joseph Louis Lagrange, the greatest mathematician of the 18th century, was born at Turin on January 25, 1736, and died at Paris on April 10, 1813. His father, who had the charge of the Sardinian military chest, was of good social position and wealthy, but before his son grew up he had lost most of his property in speculations, and young Lagrange had to rely for his position on his own abilities. He was educated at the College of Turin, but it was not until he was 17 that he shewed any taste for mathematics, his interest in the subject being first excited by a memoir by Halley, across which he came by accident. Alone and unaided, he threw himself into mathematical studies, and at the end of a year's incessant toil he was already an accomplished mathematician, and was made a lecturer in the artillery school. The first of these labours was his letter, written when he was still only 19, to Euler, in which he solved the isoperimetrical problem which for more than half a century had been the subject of discussion. To effect a solution in which he sought to determine the form of a function so that a formula in which it entered should satisfy a certain condition, he enunciated the principles of the calculus of variations. Euler recognized the generality of the method adopted, and its superiority to that used by himself, and with rare courtesy he withheld a paper that he had previously written which covered some of the same ground, in order that the young Italian might have time to complete his work and claim the undisputed invention of the new calculus. The name of this branch of analysis was suggested by Euler. This memoir at once placed Lagrange in the front rank of mathematicians then living. In 1758 Lagrange established with the aid of his pupils a society which was subsequently incorporated as the Turin Academy, and in the 5 volumes of its Transactions, usually known as the Miscellanea Turinensia, most of his early writings are to be found. Many of these are elaborate works. The first volume contains a memoir of the theory of the propagation of sound, and in this he indicates a mistake made by Newton, obtains a general differential equation for the motion, and integrates it for motion in a straight line. This volume also contains the complete solution of the problem of a string vibrating transversely. In this paper he points out a lack of generality in the solutions previously given by Taylor, D'Alembert, and Euler, and arrives at the conclusion that form of a curve at any time t is given by the equation y equals a sine mx sine nt. The article concludes with a masterly discussion of echoes, beats, and compound sounds. Other articles in this volume are on recurring series, probabilities, and the calculus of variations. The second volume, containing a long paper embodying the results of several memoirs in the first volume on the theory and notation of the calculus of variations, and he illustrates its use by deducing the principle of least action and also by solutions of various problems in dynamics. The third volume includes a solution of several dynamical problems by means of the calculus of variations, some papers on the integral calculus, a solution of Fermat's problem mentioned above, and on the general differential equations of motion for 3 bodies moving under their mutual attractions. In 1761 Lagrange stood without a rival as the foremost mathematician living, but the unceasing labour of the preceding 9 years had seriously affected his health, and the doctors refused to be responsible for his reason or life unless he would take rest and exercise. Although his health was temporarily restored, his nervous system never quite recovered its tone, and henceforth he constantly suffered from attacks of profound melancholy. The next work he produced was in 1764 on the libration of the moon, and an explanation as to why the same face was always turned to the earth, a problem which he treated by aid of virtual work. His solution is especially interesting as containing the germ of the idea of generalized equations of motion, equations which he first formally proved in 1780. He now started to go on a visit to London, but on the way fell ill at Paris. There he was received with the most marked honour, and it was with regret that he left the brilliant society of that city to return to his provincial life at Turin. His further stay in Piedmont was however short. In 1766 Euler left Berlin, and Frederick the Great immediately wrote expressing the wish of the greatest king in Europe to have the greatest mathematician in Europe resident in his court. Lagrange accepted the offer and spent the next 20 years at Prussia, where he produced not only the long series of memoirs published at the Berlin and Turin Transactions, but his monumental work Mécanique analytique. His residence at Berlin commenced with an unfortunate mistake. Finding most of his colleagues married, and assured by their wives that it was the only way to be happy, he married. His wife soon died, but the union was not a happy one. Lagrange was a favourite of the king, who used frequently to discourse to him on the advantage of perfect regularity of life. The lesson went home, and thenceforth Lagrange studied his mind and body as though they were machines, and found by experiment the exact amount of work which he was able to do without breaking down. Every night he set himself a definite task for the next day, and on completing any branch of a subject he wrote a short analysis to see what points in the demonstrations or in the subject matter were capable of improvement. He always thought out the subject of his papers before he began to compose them, and usually wrote them straight off without a single erasure or correction. His mental activity during these 20 years was amazing. Not only did he produce his splendid Mécanique analytique, but he contributed between 100 and 200 papers to the academies of Berlin, Turin, and Paris. Some of these are complete treatises, and all without exception are of a high order of excellence, except for a short time when he was ill, and produced on an average about one memoir a month. Of these I note the following as among the most important. First, his contributions to the fourth and fifth volumes, 1766 to 1773, of the Miscellanea Taurinensia, of which the most important was the one in 1771, in which he discussed how numerous astronomical observations should be combined so as to give the most probable result. And later his contributions to the first two volumes, 1784 to 1785, of the Transactions of the Turin Academy, to the first of which he contributed a paper on the pressure exerted by fluids in motion, and to the second an article on integration by infinite series, and the kind of problems for which it is suitable. Most of the memoirs sent to Paris were on astronomical questions, and among these I ought particularly to mention his memoir on the Jovian system in 1766, his essay on the problem of the three bodies in 1772, his work on the secular equation of the moon in 1773, and his treatise on cometary perturbations in 1778. These were all written on subjects proposed by the French Academy, and in each case the prize was awarded to him. The greater number of his papers during the same time were, however, contributed to the Berlin Academy. Several of them deal with questions on algebra. In particular I may mention 1. His discussion of the solution of indeterminate equations on integers in 1770, with special notice of indeterminate quadratics in 1769. 2. His tract on the theory of elimination, 1770. 3. His memoirs on the general process for solving an algebraical equations of any degree, 1770 and 1771. This method fails for equations of an order above the fourth, because then it involves a solution of an equation of higher dimensions than the one proposed, but it gives all the solutions of his predecessors as modifications of a single principle. He found, however, the complete solution of a binomial equations of any degree. And fourth, lastly, in 1773 he treated of determinants of the second and third order. Several of his early papers also deal with questions connected with the neglected but singularly fascinating subject of the theory of numbers. Among these are 1. His proof of the theorem that every integer which is not a square can be expressed as a sum of either 2, 3, or 4 integral squares, 1770. His proof of Wilson's theorem that if n be prime, then n-1 factorial plus 1 is always a multiple of n, 1771. 3. His memoirs of 1773, 1775, and 1777, which give the demonstrations of several results enunciated by Fermat and not previously proved. 4. And lastly, his method for determining the factors of numbers of the form x squared plus ay squared. There are also numerous articles on various points of analytical geometry. In 2 of them, in 1792 and 1793, he reduced the equations of the quadrics or conicoids to their canonical forms. During the years from 1772 to 1785 he contributed a long series of memoirs which created the science of differential equations, at any rate as far as partial differential equations are concerned. I do not think that any previous writer had done anything beyond considering equations of some particular form. A large part of these results were collected in the second edition of Euler's integral calculus, which was published in 1794. His papers on mechanics require no separate mention here, as the results arrived at are embodied in the Mécanique analytique, which is described below. Lastly, there are numerous memoirs on problems in astronomy. Of these, the most important are the following. 1. The Attraction of Ellipsoids, 1773. This is founded on Maclaurin's work. 2. On the Secular Equation of the Moon, 1773. Also noticeable for the earliest introduction of the idea of the potential. The potential of a body at any point is the sum of the mass of every element of the body when divided by its distance from the point. Lagrange showed that if the potential of a body at an external point were known, the attraction in any direction could be at once found. The theory of the potential was elaborated in a paper sent to Berlin in 1777. 3. On the motion of the nodes of a planet's orbit, 1774. 4. On the stability of planetary orbits, 1776. 5. Two memoirs in which the method of determining the orbit of a comet from 3 observations is completely worked out, 1778 and 1783. This is not indeed proved practically available, but his system of calculating the perturbations by means of mechanical quadratures has formed the basis of most subsequent researches on the subject. 6. His determination of the secular and periodic variations of the elements of the planets, 1781 to 1784. The upper limits assigned for these agree closely with those obtained later by Leverrier, and he proceeded as far as the knowledge then possessed of the masses of the planets permitted. 7. 3 memoirs on the method of interpolation, 1783, 1792, and 1793. The part of finite differences dealing therewith is now in the same stage as that in which Lagrange left it. Over and above these various papers, he composed his great treatise Mécanique analytique. In this he lays down the law of virtual work, and from that one fundamental principle by the aid of the calculus of variations he deduces the whole of mechanics, both of solids and fluids. The object of the book is to shew that the subject is implicitly included in a single principle, and to give the general formulae from which any particular result can be obtained. The method of generalized coordinates by which he obtained this result is perhaps the most brilliant result of his analysis. Instead of following the motion of each individual part of a material system, as D'Alembert and Euler had done, he shewed that if we determine its configuration by a sufficient number of variables, whose number is the same as that of the degrees of freedom possessed by the system, then the kinetic and potential energies of the system can be expressed in terms of these, and the differential equations of motions then deduced by simple differentiation. For example, in dynamics of a rigid system, he replaces the consideration of the particular problem by the general equation, which is now usually written in the form of d by dt times the partial derivative of capital T with respect to theta minus the partial derivative of capital T with respect to theta plus the partial derivative of v with respect to theta equals 0. Amongst other minor theorems here given, I may mention the proposition that the kinetic energy imparted by given impulses to a material system under given constraints is a maximum, and the principle of least action. All the analysis is so elegant that Sir William Rowan Hamilton said the work could be only described as a scientific poem. It may be interesting to note that Lagrange remarked that the mechanics was really a branch of pure mathematics analogous to a geometry of 4 dimensions, namely the time and the 3 coordinates of the point in space, and it is said that he prided himself that from the beginning to the end of the work there was not a single diagram. At first no printer could be found who would publish the book, but Legendre at last persuaded a Paris firm to undertake it, and it was issued under his supervision in 1788. In 1787 Frederick died, and Lagrange, who had found the climate of Berlin trying, gladly accepted the offer of Louis XVI to migrate to Paris. He received similar invitations from Spain and Naples. In France he was received with every mark of distinction, and special apartments in the Louvre were prepared for his reception. For the first 2 years of his residence here he was seized with an attack of melancholy, and even the printed copy of his Mécanique, on which he had worked for a quarter of a century, lay for more than 2 years unopened on his desk. Curiosity as to the results of the French Revolution first stirred him out of his lethargy, a curiosity which soon turned to alarm as the Revolution developed. It was about the same time, 1792, that the unaccountable sadness of his life and timidity moved the compassion of a young girl who insisted on marrying him, and proved a devoted wife to whom he became warmly attached. Although the decree of October 1793, which ordered all foreigners to leave France, specially exempted him by name, he was preparing to escape when he was offered the presidency of the Commission for the Reform of Weights and Measures. The choice of the units finally selected was largely due to him, and it was mainly owing to his influence that the decimal subdivision was accepted by the Commission of 1799. The general idea of the decimal system was taken from a work by Thomas Williams entitled Method for Fixing a Universal Standard for Weights and Measures, published in London in 1788. This almost unknown writer has hardly received the credit due to his suggestion. Though Lagrange had determined to escape from France while there was yet time, he was never in any danger, and the different revolutionary governments, and at a later time Napoleon, loaded him with honours and distinctions. A striking testimony to the respect in which he was held was shewn in 1796 when the French commissary in Italy ordered to attend in full state on Lagrange's father and tender the congratulations of the Republic on the achievements of his son, who had done honour to all mankind by his genius, and whom it was the special glory of Piedmont to have produced. In 1795 Lagrange was appointed to a mathematical chair at the newly established École Normale, which only enjoyed a brief existence of 4 months. His lectures here were quite elementary and contained nothing of any special importance, but they were published because the professors had to pledge themselves to the representatives of the people and to each other neither to read nor to repeat from memory, and the discourses were ordered to be taken down in shorthand in order to enable the deputies to see how the professors acquitted themselves. On the establishment of the École Polytechnique in 1797, Lagrange was made a professor, and his lectures there are described by mathematicians who had the good fortune to be able to attend them as almost perfect both in form and matter. Beginning with the merest elements, he led his hearers on until, almost unknown to themselves, they were themselves extending the bounds of the subject. Above all, he impressed on his pupils the advantage of always using general methods expressed in a symmetrical notation. His lectures on the differential calculus form the basis of his Théorie des fonctions analytiques, which was published in 1797. This work is the extension of an idea contained in a paper he had sent to the Berlin Memoirs in 1772, and its object is to substitute for the differential calculus as a group of theorems based on the development of algebraic functions in series. A somewhat similar method had been previously used by John Landon in his residual analysis, published in London in 1758. Lagrange believed that he could thus get rid of those difficulties connected with the use of infinitely large or infinitely small quantities which philosophers professed to see in the usual treatment of the differential calculus. The book is divided into 3 parts. Of these, the first treats of the general theory of functions, and gives an algebraic proof of Taylor's theorem, the validity of which is, however, to open the question. The second deals with applications to geometry, and the third with applications to mechanics. Another treatise on the same lines was his Leçons sur le calcul des fonctions, issued in 1804. These works may be considered as the starting point for the researches of Cauchy and Jacobi. At a later period Lagrange reverted to the use of infinitesimals in preference to founding the differential calculus on a study of algebraic forms, and in the preface to the second edition of the Mécanique, which was issued in 1811, he justifies their use and concludes by saying that when we have grasped the spirit of the infinitesimal method and have verified the exactness of its results either by the geometrical method of prime and ultimate ratios or by the analytical method of derived functions, we may employ infinitely small quantities as a sure and valuable means of shortening and simplifying our proofs. His Résolution des équations numériques, published in 1798, was also the fruit of his lectures at the Polytechnic. In this he gives the method of approximating to the real roots of an equation by means of continued fractions, and enunciates several other theorems. In a note at the end he shews how Fermat's theorem that a to the power of p minus 1 is defined as 0 mod p, where p is prime and a is prime to p, combined with a certain suggestion due to Gauss, may be applied to give the complete algebraical solution of any binomial equation. He also here explains how the equation whose roots are the squares of the differences of the roots of the original equation may be used so as to give considerable information so as to the position and nature of those roots. The theory of the planetary motions had formed the subject of some of the most remarkable of Lagrange's Berlin papers. In 1806 the subject was reopened by Poisson, who, in a paper read before the French Academy, shewed that Lagrange's formula led to certain limits for the stability of the orbits. Lagrange, who was present, now discussed the whole subject afresh, and in a memoir communicated to the Academy in 1808 explained how by the variation of arbitrary constants the periodical and secular inequalities of any system of mutually interacting bodies could be determined. In 1810 Lagrange commenced a thorough revision of the Mécanique analytique, but he was able to complete only about two-thirds of it before his death. In appearance he was of medium height and slightly formed, with pale blue eyes and a colourless complexion. In character he was nervous and timid. He detested controversy, and to avoid it willingly allowed others to take the credit for what he had himself done. Lagrange was above all a student of pure mathematics. He sought and obtained far-reaching abstract results, and was content to leave the applications to others. Indeed, no considerable part of the discoveries of his great contemporary Laplace consists of the applications of the Lagrangian formulae to the facts of nature. For example, Laplace's conclusions on the velocity of sound and the secular acceleration of the moon are implicitly involved in Lagrange's results. The only difficulty in understanding Lagrange is that of the subject matter and of the extreme generality of his processes, but his analysis is as lucid and luminous as it is symmetrical and ingenious. A recent writer speaking of Lagrange says truly that he took a prominent part in the advancement of almost every branch of pure mathematics. Like Diophantus and Fermat, he proposed a special genius for the theory of numbers, and in this subject he gave solutions of most of the problems which had been proposed by Fermat, and added some theorems of his own. He created the calculus of variations. To him too the theory of differential equations is indebted for its position as a science rather than as a collection of ingenious artifices for the solution of particular problems. To the calculus of finite differences he contributed the formula of interpolation which bears his name. But above all he impressed on mechanics, which it will be remembered he considered a part of pure mathematics, that generality and completeness towards which his labours invariably tended. End of section 31. Recording by Paul King, Oakville, Ontario. pjk.scripps.mit.edu/pkj
Chapter 18, Part 2 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj. A Short Account of the History of Mathematics by Rouse. Chapter 18. Leibniz and the Mathematicians of the First Half of the 18th Century, Part 3. Laplace. Pierre-Simon Laplace was born at Beaumont-en-Auge in Normandy on March 23, 1749, and died at Paris on March 5, 1827. He was the son of a small cottager or perhaps a farm labourer, and owed his education to the interest excited in some wealthy neighbours by his abilities and engaging presence. Very little is known of his early years, for when he became distinguished he held himself aloof from both his relatives and from those who had assisted him. A similar pettiness of character marked many of his actions. It would seem that from a pupil he became an usher in the school at Beaumont, but having procured a letter of introduction to D'Alembert, he went to Paris to push his fortune. A paper on the principles of mechanics excited D'Alembert's interest, and on his recommendations a place in the military school was offered to Laplace. Secure of a competency, Laplace now threw himself onto the original research, and in the next 17 years, 1771 to 1787, he produced much of his original work in astronomy. This commenced with a memoir read before the French Academy in 1773, which he shewed that the planetary motions were stable, and carried the proof as far as the cubes of the eccentricities and inclinations. This was followed by several papers on points in the integral calculus, finite differences, differential equations, and astronomy. During the years 1784 to 1787 he produced some memoirs of exceptional power. Prominent among those is one read in 1784 and reprinted in the third volume of the Mécanique Céleste, in which he completely determined the attraction of a spheroid on a particle outside it. This is memorable for the introduction into analysis of spherical harmonics or Laplace's coefficients, and also for the development of the use of potential, a name first given by Green in 1828. If the coordinates of 2 points be r mu omega and r prime mu prime omega prime, and r prime is not less than r, the reciprocal of the distance between them can be expanded in powers of r divided by r prime, and the respective coefficients are Laplace coefficients. Their utility arises from the fact that every function of the coordinates of a point on a sphere can be expanded in a series of them. It should be stated that the similar coefficients for space of 2 dimensions, together with some other properties, had previously been given by Legendre in a paper sent to the French Academy in 1783. Legendre had good reason to complain of the way in which he was treated in this manner. This paper is also remarkable for the development of the idea of the potential, which was appropriated from Lagrange, who had used it in his memoirs of 1773, 1777, and 1780. Laplace shewed that the potential always satisfies the differential equation del squared v equals the second partial derivative of the voltage with respect to x plus the second partial derivative of the voltage with respect to y plus the second partial derivative of the voltage with respect to z equals 0, and on this result his subsequent work on attractions was based. The quantity del squared v had been termed the concentration of v, and its value at any point indicates the excess of the value of v over its mean value in the neighbourhood of the point. Laplace's equation, or the more general form del squared v equals negative 4 pi rho, appears in all branches of mathematical physics. According to some writers, this follows at once from the fact that del squared is a scalar operator. or the equation may represent analytically some general law of nature which has not yet been reduced to words, or possibly, I have sometimes thought, it might be regarded by a Kantian as the outward sign of one of the necessary forms through which all phenomena are perceived. This memoir was followed by another on planetary inequalities, which was presented in 3 sections in 1784, 1785, and 1786. This deals mainly with the explanation of the great inequality of Jupiter and Saturn. Laplace shewed by general considerations that the mutual action of two planets could never largely affect the eccentricities and inclinations of their orbits, and that the peculiarities of the Jovian system were due to the near approach to commensurability of the mean motions of Jupiter and Saturn. Further developments of these theorems on planetary motion were given in his 2 memoirs of 1788 and 1789. It was on these data that Delambre computed his astronomical tables. The year 1787 was rendered memorable by Laplace's explanation and analysis of the relation between the lunar acceleration and the secular changes in the eccentricity of the Earth's orbit. This investigation completed the proof of the stability of the whole solar system on the assumption that it consists of a collection of rigid bodies. All the memoirs above alluded to were presented to the French Academy, and they are printed in the Mémoires présentés par divers savants. Laplace now set himself the task to write a work which should offer a complete solution of the great mechanical problem presented by the solar system, and bring theory to coincide so closely with observation that empirical equations should no longer find a place in astronomical tables. The result is embodied in the Exposition du système du monde and the Mécanique céleste. The former was published in 1796 and gives a general explanation of the phenomena with a summary of the history of astronomy, but omits all details. The nebular hypothesis was here enunciated. According to this hypothesis, the solar system has been evolved from a globular mass of incandescent gas rotating around an axis through its center of mass. As it cooled, this mass contracted and successive rings broke off from its outer edge. These rings in their turn cooled and finally condensed into the planets, while the Sun represents the central core which was still left. Certain corrections required by modern science were added by M. Roche, and recently the theory has been discussed critically by R. Wolf. The arguments against the hypothesis are summed up in Fay's Origine du Monde, Paris, 1884. Where an ingenious modification of the hypothesis is proposed, by which the author attempts to explain the peculiarities of the axial rotation of Neptune and Uranus, and the retrograde motion of the satellites of the latter planet. Perhaps modern opinion is inclined to attribute the separation of the various members of the planetary system to tidal friction rather than to the successive separation and condensation of nebular rings. But the subject is one of great difficulty. According to the rule published by Titus of Wittenberg in 1766, but generally known as Bode's law, from the fact that attention was called to it by Johann Ellet Bode in 1778, the distances of the planets from the Sun are nearly in the ratio of the numbers 0 plus 4, 3 plus 4, 6 plus 4, 12 plus 4, etc., and the n minus 2th term being 2 to the power n times 3 with 4 added. It would be an interesting fact if this could be deduced from either the nebular or the tidal hypothesis, but so far as I am aware, only one serious attempt to do so has been made, and the conclusion was that the law was not sufficiently exact to be more than a convenient means of remembering the general result. The substance of Laplace's hypothesis had been published by Kant in 1755 in his Allgemeine Naturgeschichte, but it is probable that Laplace was not aware of this. This historical summary procured for its author the honour of admission to the 40 of the French Academy. It is commonly esteemed one of the masterpieces of French literature, though it is not altogether reliable for the later periods of which it treats. The full analytical discussion of the solar system is given in the Mécanique Céleste, published in 5 volumes, volumes 1 and 2 in 1799, volume 3 in 1802, volume 4 in 1805, and volume 5 in 1825. An analysis of the contents is given in the English Cyclopedia. The first 2 volumes contain methods for calculating the motions of the planets, determining their figures, and resolving tidal problems. The 3rd and 4th volumes contain the application of these methods and also several astronomical tables. The 5th volume is mainly historical, but it gives as appendices the results of Laplace's latest researches. Laplace's own investigations embodied in it are so numerous and valuable that it is regrettable to have to add that many results are appropriated from writers with scanty or no acknowledgement, and the conclusions, which have been described as the organized result of a century of patent toil, are generally mentioned as if they were due to Laplace, and it is said, for I have not looked up into the matter myself, that the praise which he lavishes on Newton and Clairaut is only the cloak under which he appropriates the work of other less known writers. The Mécanique Céleste is by no means easy reading. Biot, who assisted Laplace in revising it for the press, says that Laplace himself was frequently unable to recover the details in the chain of reasoning, and, if satisfied that the conclusions were correct, he was content to insert the constantly recurring formula "il était à voir." The best tribute to the excellency of the work is that it left very little for his successors to add. It is not only the translation of the Principia into the language of the differential calculus, but it also completes part of which Newton had been unable to fill in the details. M. Tisserand's recent work may be considered as a continuation of Laplace's treatise. Laplace went in state to beg Napoleon to accept a copy of his work, and the following account of the interview is well authenticated, and so characteristic of all parties concerned that I quote it in full. Someone had told Napoleon that the book contained no mention of the name of God. Napoleon, who was fond of putting embarrassing questions, received it with the remark, "Monsieur Laplace, they tell me you have written this large book on the system of the universe, and have never even mentioned its creator." Laplace, who, though most supple of politicians, was as stiff as a martyr on every point of his philosophy, drew himself up and answered bluntly, "Je n'avais pas besoin de cette hypothèse-là." Napoleon, greatly amused, told this reply to Lagrange, who exclaimed, "Ah, c'est une belle hypothèse! Ça explique beaucoup de choses." In 1812 Laplace issued his Théorie analytique des probabilités. The theory is stated to be only common sense expressed in mathematical language. The method of estimating the ratio of the number of favourable cases to the whole number of possible cases has been indicated by Laplace in a paper written in 1779. It consists in treating the successive values of any function as the coefficients in the expansion of another function with reference to a different variable. The latter is therefore called the generating function of the former. Laplace then shews how by means of interpolation these coefficients may be determined from the generating function. Next he attacks the converse problem, and from the coefficients he finds the generating function. This is offered by the solution of an equation in finite differences. The method is cumbersome, and in consequence of the increased power of analysis is now rarely used. A summary of Laplace's reasoning is given in the article on probability in his Encyclopaedia Metropolitana. This treatise includes an exposition of the method of least squares, which is a remarkable testimony to Laplace's command over the process of analysis. The method of least squares for the combination of numerous observations had been given empirically by Gauss and Legendre, but the 4th chapter of this work contains a formal proof of it, on which the whole of the theory of errors has been since based. This was effected only by a most intricate analysis, specially invented for the purpose, but the form in which it is presented is so meagre and unsatisfactory that in spite of the uniform accuracy of the results, it was at one time questioned whether Laplace had actually gone through the difficult work he so briefly and often incorrectly indicates. In 1819, Laplace published a popular account of his work on probability. This book bears the same relation to his Théorie des probabilités that the Système du monde does to the Mécanique céleste. Amongst the minor discoveries of Laplace in pure mathematics, I may mention his discussion simultaneously with Vandermonde of the general theory of determinants in 1772. His proof that every equation of an even degree must have at least one real quadratic factor, his reduction of the solution of linear differential equations to definite integrals, and his solution to the linear partial equation of the second order. He was also the first to consider the difficult problems involved in the equations of mixed differences, and to prove that the solution of an equation in finite differences of the first degree and the second order might always be obtained in the form of a continued fraction. Besides these original discoveries, he determined in his theory of probabilities the values of a number of the more common definite integrals, and in the same book gave the general proof of the theorem enunciated by Lagrange for the development of any implicit function in a series by means of differential coefficients. In theoretical physics, the theory of capillary attraction is due to Laplace, who accepted the idea propounded by Hauksbee in the Philosophical Transactions for 1709, that the phenomenon was due to a force of attraction which was insensible at sensible distances. The part which deals with the action of a solid on a liquid and the mutual actions of two liquids was not worked out thoroughly, but ultimately was completed by Gauss. Newman later filled in a few details. In 1862, Lord Kelvin, Sir William Thomson, shewed that if we assume the molecular constitution of matter, the laws of capillary attraction can be deduced from the Newtonian law of gravitation. Laplace in 1816 was the first to point out explicitly why Newton's theory of vibratory motion gave an incorrect value for the velocity of sound. The actual velocity is greater than that calculated by Newton in consequence of the heat developed by the sudden compression of air, which increases the elasticity and therefore the velocity of sound transmitted. Laplace's investigations in practical physics were confined to those carried on by him jointly with Lavoisier in the years 1782 and 1784 on the specific heat of various bodies. Laplace seems to have regarded analysis as merely a means of attacking physical problems, though the ability with which he invented the necessary analysis is almost phenomenal. As long as his results were true, he took but little trouble to explain the steps by which he arrived at them. He never studied elegance or symmetry in his processes, and it was sufficient for him if he could by any means solve the particular question he was discussing. In these respects he stands in marked contrast to his great contemporary Lagrange. It would have been well for Laplace's reputation if he had been content with his scientific work, but above all things he coveted social fame. The skill and rapidity with which he managed to change his politics as occasion required would be amusing if they had not been so servile. As Napoleon's power increased, Laplace abandoned his republican principles, which, since they had faithfully reflected the opinions of the party in power, had themselves gone through numerous changes, and begged for the First Council to give him the post of Minister of the Interior. Napoleon, who desired the support of men of science, accepted the offer, but a little less than 6 weeks saw the close of Laplace's political career. Napoleon's memorandum on the subject is as follows.
Géomètre de premier rang, Laplace ne tarda à se montrer administrateur plus que médiocre. Dès son premier travail, nous reconnûmes que nous étions trompés. Laplace ne cessant aucune question sous son véritable point de vue. Il cherchait des subtilités partout, n'avait que des idées problématiques,
portait enfant l'esprit des infiniment petits jusque dans l'administration. Although Laplace was expelled from office, it was desirable to retain his allegiance. He was accordingly raised to the Senate, and to the third volume of the Mécanique Céleste he prefixed a note that of all the truths therein contained, the most precious to the author was the declaration he thus made of his devotion toward the peacemaker of Europe. In copies sold after the Restoration, this was struck out. In 1814 it was evident that the empire was falling. Laplace hastened to tender his services to the Bourbons, and on the Restoration was rewarded with the title of Marquis. The contempt that his more honest colleagues felt for his conduct in the matter may be read in the pages of Paul Louis Courier. His knowledge was useful on the numerous scientific commissions on which he served, and probably accounts for the manner in which his political insincerity was overlooked. But the pettiness of his character must not make us forget how great were his services to science. That Laplace was vain and selfish is not denied by his warmest admirers. His conduct to the benefactors of his youth and his political friends was ungrateful and contemptible, while his appropriation of the results of those who were comparatively unknown seems to be well established and is absolutely indefensible. Of those whom he thus treated, three subsequently rose to distinction, Legendre and Fourier in France and Young in England, and never forgot the injustice of which they had been the victims. On the other side, it may be said that on some questions he shewed independence of character, and he never concealed his views on religion, philosophy, or science, however distasteful they might be to the authorities in power. It should be also added that towards the close of his life, and especially to the work of his pupils, Laplace was both generous and appreciative, and in one case suppressed a paper of his own in order that a pupil might have the sole credit of the discovery. Legendre. Adrien Marie Legendre was born at Toulouse on September 18, 1752, and died at Paris on January 10, 1833. The leading events of his life are very simple and may be summed up briefly. He was educated at the Mazarin College in Paris, appointed the professor at the military school in Paris in 1777, was a member of the Anglo-French Commission of 1787 to connect Greenwich and Paris geodetically, served on several of the public commissions from 1792 to 1810, was made a professor at the Normal School in 1795, and subsequently held a few minor government appointments. The influence of Laplace was steadily exerted against his obtaining office or public recognition, and Legendre, who was a timid student, accepted the obscurity to which the hostility of his colleague condemned him. Legendre's analysis is of a high order of excellence, and is second only to that produced by Lagrange and Laplace, though it is not so original. His chief works are his Géométrie, his Théorie des Nombres, and his Calcul intégral, and his Fonctions elliptiques. These include the results of his various papers on these subjects. Besides these he wrote a treatise which gave the rule for the method of least squares, and two groups of memoirs, one on the theory of attractions and the other on geodetical operations. The memoirs on attractions are analyzed and discussed in Todhunter's History of the Theory of Attraction. The earliest of these memoirs, presented in 1783, was on the attraction of spheroids. This contained the introduction of Legendre's coefficients, which are sometimes called circular or zonal harmonics, and which are particular cases of Laplace's coefficients. It also includes the solution of a problem in which the potential is used. The second memoir was communicated in 1784, and is of the form of equilibrium of a mass of rotating liquid, which is approximately spherical. The third, written in 1786, is on the attraction of confocal elliptoids. The fourth is on the figure which a fluid planet would assume, and its law of density. His papers on geodesy are 3 in number and were presented to the Academy in 1787 and 1788. The most important result is that by which a spherical triangle may be treated as a plane, provided certain corrections are applied to the angles. In connection with this subject he paid considerable attention to geodesics. The method of least squares was enunciated in his Nouvelle Méthode, published in 1806, to which supplements were added in 1810 and 1820. Gauss independently had arrived at the same result and had used it in 1795 and published it and the law of facility in 1809. Laplace was the earlier writer to give a proof of it. This was in 1812. On the other books produced by Legendre, the one most widely known is his Éléments de géométrie, which was published in 1794 and was generally adopted on the continent as a substitute for Euclid. The later editions contain the elements of trigonometry and proofs of the irrationality of pi and pi squared. An appendix on the difficult question of the theory of parallel lines was issued in 1803 and is bound up with most of the subsequent editions. His Théorie des Nombres was published in 1798 and appendices were added in 1816 and 1825. The third edition, issued in 2 volumes in 1830, includes the results of his various later papers and still remains a standard work on the subject. It may be said that he here carried the subject as far as was possible by the application of ordinary algebra, but he did not realize that it might be regarded as a higher arithmetic and so form a distinctive subject in mathematics. The law of quadratic reciprocity, which connects any 2 odd primes, is first proved in this book, but the result had been enunciated in a memoir of 1785. Gauss called the proposition the gem of arithmetic, and no less than 6 separate proofs are to be found in his works. The theorem is as follows. If p be a prime and n be a prime to p, then we know that the remainder when the square root of n to the power of p minus 1 is divided by p is either plus 1 or minus 1. Legendre denoted this remainder by n over p. When the remainder is plus 1, it is possible to find a square number which, when divided by p, leaves a remainder n, that is, n is a quadratic residue of p. When the remainder is minus 1, there exists no such square number, and n is a non-residue of p. The law of quadratic reciprocity is expressed by the theorem that if a and b be any odd primes, then the Legendre symbol a over b times the Legendre symbol b over a is the fourth root of minus 1 to the power of a minus 1 times b minus 1. Thus, if b is a residue of a, then a is also a residue of b, unless both the primes of a and b are of the form 4 times m plus 3. In other words, if a and b be odd primes, then we know that the square root of a to the power of b minus 1 is defined as plus or minus 1 mod b, and the square root of b to the power of a minus 1 is defined as plus or minus 1 mod a. But Legendre's law and the 2 ambiguities will be either both positive or both negative unless a and b are both of the form 4m plus 3. Thus, if one odd prime be a non-residue of another, then the latter will be a non-residue of the former. Gauss and Kummer have subsequently proved similar laws of cubic and biquadratic reciprocity, and an important branch of the theory of numbers has been based on these researches. This work also contains the useful theorem by which, when it is possible, an indeterminate equation of the second degree can be reduced to the form ax squared plus by squared plus cz squared equals 0. Legendre too here discussed the forms of numbers which can be expressed as the sums of 3 squares, and he proved, article 404, that the number of primes less than n is very approximately n divided by the quantity log n minus 1.08366. The Exercice de calcul intégral was published in 3 volumes, 1811, 1817, and 1826. Of these, the third and most of the first were devoted to elliptic functions, the bulk of this being ultimately included in the Fonctions elliptiques. The contents of the remainder of the treatise are of a miscellaneous character. They include integration by series, definite integrals, and in particular an elaborate discussion of the beta and the gamma functions. The Traité des Fonctions elliptiques was issued in 2 volumes in 1825 and 1826 and is the most important of Legendre's works. A third volume was added a few weeks before his death and contains 3 memoirs of the researches of Abel and Jacobi. Legendre's investigations have commenced with a paper written in 1786 on elliptic arcs, but here and in his other papers he treated the subject merely as a branch of the integral calculus. Tables of the elliptic integrals were constructed by him. The modern treatment of the subject is founded on that of Abel and Jacobi. The superiority of their methods was at once recognized by Legendre, and almost the last act of his life was to recommend those discoveries which he knew would consign his own labours to comparative oblivion. This may serve to remind us of a fact which I wish to specially emphasize, namely, that Gauss, Abel, Jacobi, and some others of the mathematicians alluded to in the next chapter were contemporaries of the members of the French school. Pfaff. I may here mention another writer who also made a special study of the integral calculus. This was Johann Friedrich Pfaff, born in Stuttgart on December 22, 1765, and died at Halle on April 21, 1825, who was described by Laplace as the most eminent mathematician in Germany at the beginning of this century, a description which, had it not been for Gauss's existence, would have been true enough. Pfaff was the precursor of the German school, which under Gauss and his followers has largely determined the lines on which mathematics have developed during this century. He was an intimate friend of Gauss, and in fact the two mathematicians lived together at Helmstadt for the year after Gauss finished his university course in 1798. Pfaff's chief work was his unfinished Disquisitions analyticae on the integral calculus, published in 1797, and his most important memoirs were either on the calculus or on differential equations. On the latter subject, his paper read before the Berlin Academy in 1814 is still a standard authority. The creation of modern geometry. While Euler, Lagrange, Laplace, and Legendre were perfecting analysis, the members of another group of the French mathematicians were extending the range of geometry by methods similar to those previously used by Desargues and Pascal. The most eminent of those who created modern synthetic geometry was Poncelet, but the subject is also associated with the names of Monge and L. Carnot. Its development in more recent times is largely due to Steiner, von Staudt, and Cremona. Monge. Gaspard Monge was born at Bonn on May 10th, 1746, and died at Paris on July 28, 1818. He was a son of a small peddler, and was educated in the schools of the Oratorians, one of which he subsequently became an usher. A plan of Bonn which he had made fell into the hands of an officer who recommended the military authorities to admit him to their training school at Mézières. His birth, however, precluded his receiving commission in the army, but his attendance at an annex of the school where surveying and drawing were taught was tolerated, though he was told that he was not sufficiently well born to be allowed to attempt problems which required calculation. At last his opportunity came. A plan of a fortress having to be drawn from data supplied by certain observations, he did it by a geometrical construction. At first the officer in charge refused to receive it because etiquette required that not less than a certain time should be used in making such drawings, but the superiority of the method over that then taught was so obvious that it was accepted. and in 1768 Monge was made professor, on the understanding that the results of his descriptive geometry were to be a military secret confined to the officers above a certain rank. In 1780 he was appointed to a chair of mathematics in Paris, and this with several provincial appointments which he held gave him a comfortable income. The earliest paper of any special importance which he communicated to the French Academy was one in 1781 in which he discussed the lines of curvature drawn on a surface. These had been first considered by Euler in 1760 and defined as those normal sections whose curvature was a maximum or a minimum. Monge treated them as the locus of those points on the surface as which successive normals intersect, and thus obtained the general differential equation. He applied his results to the central quadrics in 1795. In 1786 he published his well-known work on statics. Monge eagerly embraced the doctrines of the Revolution. In 1792 he became Minister of the Marine and assisted the Committee of the Public Safety in utilizing science for the defense of the Republic. When the terrorists obtained power he was denounced and only escaped the guillotine by a hasty flight. On his return in 1794 he was made professor at the short-lived Normal School, where he gave lectures on descriptive geometry. The notes of these were published under a regulation alluded to above. In 1796 he went to Italy on the roving commission which was sent with orders to compel the various Italian towns to offer any pictures, sculpture, or other works of art that they might possess as a present or in lieu of contributions to the French Republic for removal to Paris. In 1798 he accepted a mission to Rome, and after executing it joined Napoleon in Egypt. Thence, after the naval and military victories at England, he escaped to France. He was then made professor at the Polytechnic School, where he gave lectures on descriptive geometry. These were published in 1800 in the form of a textbook entitled Géométrie descriptive. This work contains prepositions on the form and relative position of geometrical figures deduced by the use of transversals. The theory of perspective is considered, and this includes the art of representing in 2 dimensions geometrical objects which are of 3 dimensions, a problem which Monge usually solved by the aid of 2 diagrams, one being the plan and the other being the elevation. Monge also discussed the question as to whether, if in solving a problem certain subsidiary quantities introduced to facilitate the solution become imaginary, the validity of the solution is thereby impaired, and he shewed that the result would not be affected. On the Restoration he was deprived of his offices and honours, a degradation which preyed on his mind and which he did not long survive. Most of his miscellaneous papers are embodied in his works Application de l'algèbre à la géométrie, published in 1805, and Application de l'analyse à la géométrie, the 4th edition of which, published in 1819, was revised by him just before his death. It contains, among other results, his solution of a partial differential equation of the 2nd order. Carnot. Lazare Nicolas Marie Carnot, born at Nolay on May 13, 1753, and died at Magdeburg on August 22, 1823, was educated at Burgundy and obtained a commission at the Engineer Corps of Condé. Although in the army, he continued his mathematical studies which he felt great interest. His first work, published in 1784, was on machines. It contained a statement which foreshadows the principle of energy as applied to a falling weight, and the earliest proof of the fact that kinetic energy is lost in the collision of bodies. In the outbreak of the Revolution in 1789, he threw himself into politics. In 1793 he was elected on the Committee of Public Safety, and the victories of the French army were largely due to his powers of organization and enforcing discipline. He continued to occupy a prominent place in every successive form of government till 1796, when, having opposed to Napoleon's coup d'etat, he had to fly from France. He took refuge in Geneva, and there in 1797 issued La Métaphysique de Calcul Infinitesimal. In 1802 he assisted Napoleon, but his sincere republican convictions were inconsistent with the retention of office. In 1803 he produces Géométrie des positions. This work deals with projective rather than descriptive geometry. It also contains an elaborate discussion of the geometrical meaning of negative roots of an algebraical equation. In 1814 he offered his services to fight for France, though not for the empire, and on the Restoration he was exiled. Poncelet. Jean-Victor Poncelet, born at Metz in July 1st, 1788, and died at Paris on December 22, 1867, held a commission in the French engineers. Having been made a prisoner in the French retreat from Moscow in 1812, he occupied his enforced leisure by writing the Traité des proprietés projections des figures, published in 1822, which was long one of the best-known textbooks on modern geometry. By means of projection, reciprocation, and homologous figures, he established all the chief properties of conics and quadrics. He also treated the theory of polygons. His treatise on the practical mechanics in 1828, his memoir on water mills in 1826, and his report on the English machinery and tools exhibited at the International Exhibition held in London in 1851 deserve mention. He contributed numerous articles to Crell's journal. The most valuable of these deal with the explanation of imaginary solutions and geometrical problems by the aid of the doctrine of continuity. The development of mathematical physics. It will be noticed that Lagrange, Laplace, and Legendre mostly occupied themselves with analysis, geometry, and astronomy. I am inclined to regard Cauchy and the French mathematicians of the present day as belonging to a different school of thought to that considered in this chapter, and I place them amongst modern mathematicians. But I think that Fourier, Poisson, and the majority of their contemporaries are the lineal successors of Lagrange and Laplace. If this view is correct, it would seem that the latter members of the French school devoted themselves mainly to the application of mathematical analysis to physics. Before considering these mathematicians, I may mention the distinguished English experimental physicists who were their contemporaries and whose merits have only recently received an adequate recognition. Chief among these are Cavendish and Young. Cavendish. The Honourable Henry Cavendish, born at Nice on October 10, 1731, and died at London on February 24, 1810. His tastes for scientific research and mathematics were formed at Cambridge, where he resided from 1749 to 1753. He created experimental electricity and was one of the earliest writers to treat chemistry as an exact science. I mention him here on account of his experiment in 1798 to determine the density of the Earth by estimating its attraction as compared with that of two given lead balls. The result is that the mean density of the Earth is about 5.5 times that of water. This experiment was carried out in accordance with a suggestion which had been first made by John Michell, a fellow of Queen's College, Cambridge, who had died before he was able to carry it into effect. End of Part 32. Recording by Paul King, Oakville, Ontario. http pjk.scripts.mit.edu/pkj. Chapter 18, Part 4 of A Short Account of the History of Mathematics by Rouse. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pjk. A Short Account of the History of Mathematics by Rouse. Chapter 18. Leibniz and the Mathematicians of the First Half of the 18th Century, Part 4. Cavendish. The Honourable Henry Cavendish was born at Nice on October 10, 1731, and died in London on February 24, 1810. His tastes for scientific research and mathematics were formed at Cambridge, where he resided from 1749 to 1753. He created experimental electricity and was one of the earliest writers to treat chemistry as an exact science. I mention him here on account of his experiment in 1798 to determine the density of the earth by estimating its attraction as compared with that of two given lead balls. The result is that the mean density of the earth is about 5.5 times that of water. This experiment was carried out in accordance with a suggestion which had been first made by John Michell, a fellow of Queen's College, Cambridge, who had died before he was able to carry it into effect. Rumford. Sir Benjamin Thompson, Count Rumford, born at Concord on March 26, 1753, and died at Auteuil on August 21, 1815, was of English descent and fought on the side of the Loyalists in the American War of Secession. On the conclusion of peace he settled in England, but subsequently entered the service of Bavaria, where his military and civil powers of organization proved of great value. At a later period he again resided in England, and when there he founded the Royal Institution. The majority of his papers were communicated to the Royal Society of London. Of these the most important is his memoir, in which he shewed that heat and work are mutually convertible. Young. Among the most eminent physicists of his time was Thomas Young, who was born in Milverton on June 13, 1773, and died in London on May 10, 1829. He seems as a boy to have been somewhat of a prodigy, being well read in modern languages and literature as well as in science. He always kept up his literary tastes, and it was he who first furnished the key to decipher the Egyptian hieroglyphics. He was destined to be a doctor, and after attending lectures at Edinburgh and Göttingen, entered Emmanuel College, Cambridge, from which he took his degree in 1799, and to his stay at the university he attributed much of his future distinction. His medical career was not particularly successful, and his favourable maxim that a medical diagnosis is only a balance of probabilities was not appreciated by his patients, who looked for certainty in return for their fee. Fortunately, his private means were ample. Several papers contributed to various learned societies from 1798 onwards prove him to have been a mathematician of considerable power. But the researches which have immortalized his name are those by which he laid down the laws of interference of waves in light, and was thus able to suggest the means by which the chief difficulties in the way of acceptance of the undulatory theory of light could be overcome. Wollaston. Another experimental physicist of the same time and school was William Hyde Wollaston, who was born at Dereham on August 6, 1766, and died in London on December 22, 1828. He was educated at Caius College, Cambridge, of which society he was a fellow. Besides his well-known chemical experiments, he is celebrated for his researches on experimental optics and for the improvements which he effected in astronomical instruments. Dalton. Another distinguished writer of the same period was John Dalton, who was born in Cumberland on September 5, 1766, and died at Manchester on July 27, 1844. Dalton investigated the tension of vapours and the law of the expansion of a gas under changes of temperature. He also found the atomic theory in chemistry. It will be gathered from these notes that the English school of physicists at the beginning of this century were mostly concerned with the experimental side of the subject, but in fact no satisfactory theory could be formed without some similar careful determination of the facts. The most eminent French physicists of the same time were Fourier, Poisson, Ampère, and Fresnel. Their method of treating the subject is more mathematical than that of their English contemporaries, and the two first named were distinguished for general mathematical ability. Fourier. The first of these French physicists was Jean-Baptiste Joseph Fourier, who was born at Auxerre on March 21, 1768, and died at Paris on May 16, 1830. He was the son of a tailor and was educated by the Benedictines. The commissions in the scientific corps of the army was, as still the case in Russia, reserved for those of good birth, and being thus ineligible, he accepted a military lectureship on mathematics. He took a prominent part in his own district in promoting the revolution, and was rewarded by an appointment in 1795 in the Normal School and subsequently by a chair at the Polytechnic School. He went with Napoleon on his eastern expedition in 1798 and was made governor of Lower Egypt. Cut off from France by the English fleet, he organized the workshops on which the French army had to rely for their munitions of war. He also contributed several mathematical papers to the Egyptian Institute, which Napoleon founded at Cairo with a view of weakening English influence in the East. After the British victories and the capitulation of the French under General Menon in 1801, he returned to France and was made prefect of Grenoble, and it was while there that he made his experiments on the propagation of heat. He moved to Paris in 1816. In 1822 he published his Théorie analytique de la chaleur, in which he bases his reasoning on Newton's law of cooling, namely that the flow of heat between two adjacent molecules is proportional to the infinitely small difference of their temperatures. He states that the theory demands that the temperatures of stellar space should be between -50 degrees Celsius and -60 degrees Celsius, a conclusion which it has been as yet impossible to prove or disprove. In this work he shews that any function of a variable, whether continuous or discontinuous, can be expanded in a series of sines of multiples of the variable, a result which is constantly used in modern analysis. Lagrange had given particular cases of the theorem and had implied that the method was general, but he had not pursued the subject. Fourier left an unfinished work on determinate equations, which was edited by Navier and published in 1831. This contains much original matter. In particular, there is a demonstration of Fourier's theorem on the position of the roots of an algebraic equation. Lagrange had shewn how the roots of an algebraical equation might be separated by means of another equation whose roots were the squares of the differences of the roots of the original equation. Boudin in 1807 and 1811 had enunciated the theorem generally known by the name of Fourier, but the demonstration was clumsy and not altogether satisfactory. Fourier's proof is the same as that usually given in textbooks on the theory of equations. The final solution of the problem was given in 1829 by Jacques-Charles-François Sturm.
Sadi Carnot. Among Fourier's contemporaries who were interested in the theory of heat, the most eminent was Sadi Carnot, son of the eminent geometrician mentioned previously. Sadi Carnot was born at Paris in 1796 and died there of cholera in August 1832. He was an officer in the French army. In 1824 he issued a short work entitled Réflexions sur les puissances motrices du feu, in which he attempted to determine in what way heat produced its mechanical effect. He made the mistake of assuming that heat was material, but his essay was the commencement of the modern theory of thermodynamics. Poisson. Siméon Denis Poisson, born at Pithiviers on June 21, 1781, and died at Paris on April 25, 1840, is almost equally distinguished for his application of mathematics to mechanics and to physics. His father had been a common soldier, and on his retirement was given some small administrative post in his native village. When the revolution broke out, he appears to have assumed the government of the place, and, being left undisturbed, became a person of some local importance. The boy was put out to nurse, and he used to tell how one day his father, coming to see him, found that the nurse had gone out on pleasure bent, while she had left him suspended by a small cord to a nail fixed in the wall. This, she explained, was a necessary precaution to prevent him from perishing under the teeth of the various animals and animalcula that roamed on the floor. Poussin used to add that his gymnastic efforts carried him incessantly from one side to the other, and it was thus in his tenderest infancy that he commenced those studies on the pendulum that were there to occupy so large a part of his mature age. He was educated by his father, and destined much against his will to be a doctor. His uncle offered to teach him the art, and began by making him prick the veins of cabbage leaves with a lancet. When perfect in this, he was allowed to put on blisters, but in almost the first case he did this by himself. The patient died in a few hours, and though all the medical practitioners of the place assured him that the event was a very common one, he vowed he would have nothing more to do with the profession. Returning home, he found amongst the official papers sent to his father a copy of the questions set at the Polytechnic school, and at once found his career. At the age of 17 he entered the Polytechnic, and his abilities excited the interest of Lagrange and Laplace, whose friendship he retained to the end of their lives. A memoir on finite differences, which he wrote when only 18, was reported on so favourably by Legendre that it was ordered to be published in the Recueil des Savants Étrangers. Directly he had finished the course, he was made a lecturer at the school, and he continued through his life to hold various government scientific posts and professorships. He was somewhat of a socialist, and remained a rigid republican till 1815, with a view to making another empire impossible. He joined the Legitimists. He took, however, no active part in politics, and made the study of mathematics his amusement as well as his business. His works and memoirs are between 300 and 400 in number. The chief treatises which he wrote were his Traité de mécanique, 2 volumes, 1811 and 1833, which was long, a standard work; his Théorie nouvelle de l'action capillaire in 1831, his Théorie mathématique de la chaleur in 1835, to which a supplement was added in 1837, and his Recherches sur la probabilité des jugements in 1837. He had intended, if he had lived, to write a work which should cover all mathematical physics, and in which these would have been incorporated. Of his memoirs on the subject of pure mathematics, the most important are those on definite integrals, and the Fourier's series. These are to be found on the Journal Polytechnique from 1813 to 1823, and in the Mémoires de l'Académie for 1823. Their application to physical problems constituting one of his chief claims to distinction, his essay on the calculus of variations, Mémoires de l'Académie, 1833, and his papers on the probability of the mean results of observations, Connaissance des temps, 1827, and following years. Most of his memoirs were published in the 3 periodicals here mentioned. Perhaps the most remarkable of his memoirs on applied mathematics are those on the theory of electrostatics and magnetism, which originated a new branch of mathematical physics. He supposed that the results were due to the attractions and repulsions of imponderable particles. The most important of those on physical astronomy are the 2 read in 1806, printed in 1809, on the secular inequalities of the mean motions of the planets, and on the variations of arbitrary constants introduced into the solutions of questions on mechanics. In those, Poisson discusses the question of the stability of the planetary orbits, which Legendre had already proved to the first degree of approximation for the distributing forces, and shews that the result can be extended to the third order of small quantities. These were the memoirs which led to Lagrange's famous memoir of 1808. Poisson also published a paper in 1821 on the libration of the moon, and another in 1827 on the motion of the earth about its centre of gravity. His most important memoirs on the theory of attraction are one in 1829 on the attraction of spheroids, and another in 1835 on the attraction of a homogeneous ellipsoid. The substitution of the correct equation involving the potential, namely grad squared v equals negative 4 pi rho, for Laplace's form of it, pi squared v equals 0, was first published in 1813 in the Bulletin des Sciences of the Société Philomatique. Lastly, I may mention his memoir in 1825 on the theory of waves.
Ampère. André-Marie Ampère was born at Lyon in January 22, 1775, and died at Marseille on June 10, 1836. He was widely read in all branches of learning and lectured and wrote on many of them, but after the year 1809, when he was made professor of analysis at the Polytechnic School in Paris, he confined himself almost entirely to mathematics and science. His papers on the connection between electricity and magnetism were written in 1820. According to his theory, propounded in 1826, a molecule of matter which can be magnetized is traversed by a cloud of electric current, and a magnetization is produced by any cause which makes the direction of these currents in the different molecules of the body approach parallelism. Fresnel. Augustin Jean Fresnel, born at Broglie on May 10, 1788, and died at Ville d'Avray on July 14, 1827, was a civil engineer by profession, but he devoted his leisure to the study of physical optics. The undulatory theory of light, which Hooke, Huygens, and Euler had supported on a priori grounds, had been based on experiment by the researches of Young. Fresnel deduced the mathematical consequences of these experiments and explained the phenomenon of the interference of both ordinary and polarized light. Biot. Fresnel's friend and contemporary Jean-Baptiste Biot, who was born at Paris on April 21, 1774, and died there in 1862, requires a word or two in passing. Most of his mathematical work was in connection with the subject of optics, and especially with the polarization of light. His systematic works were produced within the years 1805 and 1817. A selection of his more valuable memoirs was published in Paris in 1858. Arago. François-Jean Dominique Arago was born at Estangel in the Pyrenees on February 26, 1786, and died in Paris on October 2, 1853. He was educated at the Polytechnic School, Paris, and we gather from his autobiography that however distinguished were the professors of that institution, they were remarkably incapable of imparting their knowledge or maintaining discipline. In 1804 he was made secretary to the observatory, and then from 1806 to 1809 he was engaged in measuring a meridian arc in order to determine the exact length of a meter. He was then made one of the astronomers at Paris, given a residence there, and made a professor at the Polytechnic School, where he enjoyed a marked success as a lecturer. He subsequently gave popular lectures on astronomy, which were both lucid and accurate, a combination of qualities which was rarer then than now. He reorganized the National Observatory, the management of which had long been inefficient, but in doing this he shewed himself dictatorial and passionate, and the same defects of character revealed themselves in many of the events of his life. He remained to the end a consistent republican, and after the coup d'etat of 1852, though half blind and dying, he resigned his post as an astronomer rather than take the oath of allegiance. It is to the credit of Napoleon III that he gave directions that the old man should be in no way disturbed, and that he should be left free to say and do what he liked. His earliest physical researches were on the pressure of steam at different temperatures and the velocity of sound (1818 to 1822). His magnetic observations mostly took place from 1823 to 1826. He discovered what had been called rotary magnetism and the fact that most bodies could be magnetized. These discoveries were completed and explained by Faraday. He warmly supported Fresnel's optical theories, and the two philosophers conducted together those experiments on the polarization of light which led to the inference that the vibrations of the luminiferous ether were transverse to the direction of motion, and that the polarization consisted in a resolution of rectilinear motion into components at right angles to each other. The subsequent invention of the polariscope and the discovery of rotatory polarization are due to Arago. The general idea of the experimental determination of the velocity of light in the manner subsequently effected by Fizeau and Foucault was suggested by him in 1838, but his failing eyesight prevented his arranging the details or making the experiments. It will be noticed that some of the last members of the French school were alive at a comparatively recent date, but nearly all mathematical work was done before the year 1830. They are the direct successors of the French writers who flourished at the commencement of this century, and seem to have been out of touch with the great German mathematicians of the early part of it, on whose researches much of the best work of this century is based. They are thus placed here, though their writings are in some cases of a later date than those of Gauss, Abel, Jacobi, and other mathematicians of recent times. The introduction of analysis into England. The complete isolation of the English school and its devotion to geometrical methods are the most marked features in its history during the latter half of the 18th century, and the absence of any considerable and valuable contributions to the advancement of mathematical science was a natural consequence. One result of this was that the energy of the English men of science was largely devoted to practical physics and practical astronomy, which were in consequence studied in Britain perhaps more than elsewhere. Almost the only English mathematician at the beginning of this century who used analytical methods and whose work requires mention here is Ivory, to whom the celebrated theorem of attractions is due. James Ivory was born in Dundee in 1765 and died at Douglastown on September 21, 1845. After graduating at St Andrews, he became the managing partner in a flax spinning company in Forfarshire, but continued to devote most of his leisure to mathematics. In 1804 he was made professor at the Royal Military College at Marlow, which is now moved to Sandhurst. He contributed numerous papers to the Philosophical Transactions, the most remarkable being those on attractions. In one of these, in 1809, he shewed how the attraction of a homogeneous ellipsoid on an external point is a multiple of that of another ellipsoid on an internal point. The latter can be easily obtained. He criticized Laplace's solution of the method of least squares with unnecessary bitterness, and in terms which proved his incompetence to understand it. The Cambridge Analytical School. Toward the close of the last century, the more thoughtful members of the Cambridge School of Mathematics began to recognize that their isolation from the continental contemporaries was a serious evil. The earliest attempt in England to explain the notation and methods of the calculus as used on the continent was due to Woodhouse, who stands out as the apostle of the new movement. It is doubtful if he could have brought the analytical methods into vogue by himself, but his views were enthusiastically adopted by three undergraduates, Babbage, Peacock, and Herschel, who succeeded in carrying out reforms that he had suggested. In a book which will fall into the hands of few but English readers, I may be pardoned for making space for a few remarks on these four mathematicians. The original stimulus came from French sources, and I therefore place these remarks at the close of my account of the French school. But I should add that the English mathematicians of this century at once struck out a line independent of their French contemporaries. Woodhouse. Robert Woodhouse was born at Norwich on April 28, 1773, was educated at Caius College, Cambridge, of which society he was subsequently a fellow, was Plumian professor in the university, and continued to live at Cambridge till his death on December 23, 1827. His earliest work, entitled The Principles of Analytical Calculation, was published at Cambridge in 1803. In this he explained the differential notation and strongly pressed the employment of it, but he severely criticized the methods used by continental writers and their constant assumption of non-evident principles. This was followed in 1809 by a trigonometry, plane and spherical, and in 1810 by a historical treatise on the calculus of variations and isoperimetrical problems. He next produced an astronomy, the first volume, usually bound in two, on practical and descriptive astronomy, being issued in 1812, the second volume, containing an account of the treatment of physical astronomy by Laplace and other continental writers, being issued in 1818. All these works deal critically with the scientific foundation of the subjects considered, a point which is not unfrequently neglected in modern textbooks. A man like Woodhouse, of scrupulous honour, universally respected, a trained logician, and with a caustic wit, was well fitted to introduce a new system. And the fact that when he first called attention to the continental analysis, he exposed the unsoundness of some of the usual methods of establishing it, more like an opponent than a partisan, and was politic as it was honest. Woodhouse did not exercise much influence on the majority of his contemporaries, and the movement might have died away for the time being had it not been for the advocacy of Peacock, Herschel, and Babbage, who formed an analytical society with the object of advocating the general use in the university of analytical methods and of the differential notation. Peacock. George Peacock, who was the most influential of the early members of the new school, was born at Denton on April 9, 1791. He was educated at Trinity College, Cambridge, of which society he was subsequently a fellow and tutor. The establishment of the University Observatory was mainly due to his efforts, and in 1836 he was appointed to the Lowndean Professorship of Astronomy and Geometry. In 1839 he was made Dean of Ely and resided there until his death on November 8, 1858. Although Peacock's influence on English mathematicians was considerable, he has left but few memorials to his work. But I may note that his report on recent progress and analysis 1833 commenced those valuable summaries of scientific progress which enrich many of the annual volumes of the Transactions of the British Association. Babbage. Another important member of the Analytical Society was Charles Babbage, who was born at Totnes in December 26, 1792. He entered Trinity College, Cambridge in 1810, subsequently became Lucasian professor in the university, and died in London on October 18, 1871. It was he who gave the name to the Analytical Society, which he stated was formed to advocate the principles of pure deism as opposed to the dotage of the university. In 1820 the Astronomical Society was founded mainly through his efforts, and at a later time, 1830 to 1832, he took a prominent part in the foundation of the British Association. He will be remembered for his mathematical memoirs on the calculus of functions, and in the invention of analytical machines, which could not only perform ordinary processes of arithmetic, but could tabulate the values of any functions and print the results. Herschel. The third of those who helped bring analytical methods into general use in England was the son of Sir William Herschel, 1738 to 1822. The most illustrious astronomer of the latter half of the last century, and the creator, it may be fairly said, of stellar astronomy. Sir John Frederick William Herschel was born on March 7th, 1792, and educated at St. John's College, Cambridge, and died on May 11th, 1871. His earliest original work was a paper on Coates's theorem, and it was followed by others on mathematical analysis, but his desire to complete his father's work led ultimately to his taking up astronomy. His papers on light and astronomy contain a clear exposition of the principles which underlie the mathematical treatment of those subjects. In 1813 the Analytical Society published a volume of memoirs, of which the preface and the first paper on continued products are due to Babbage, and 3 years later they issued a translation of Lacroix' Traité des élémentaires du calcul différentiel et du calcul intégral. In 1817 and again in 1819 the differential notation was used in the university examinations, and after 1820 its use was well established. The Analytical Society followed up this rapid victory by the issue in 1820 of 2 volumes of examples illustrative of the new method, one by Peacock on the differential and integral calculus, and the other by Herschel on the calculus of finite differences. Since then, English works on the infinitesimal calculus have abandoned the exclusive use of the fluxional notation. It should be noticed in passing that Lagrange and Laplace, like the majority of other modern writers, employ both the fluxional and the differential notation. It was the exclusive adoption of the former that was so hampering. Amongst those who materially assisted in extending the use of the new analysis were William Whewell (1794 1866) and George Bedell Airy (1801 1892), both fellows at Trinity College, Cambridge. The former issued in 1819 a work on mechanics, and the latter, who was a pupil of Peacock, published in 1826 in his tracts, in which the new method was applied with great success to various physical problems. The efforts of the Society were supplemented by the rapid publication of good textbooks in which analysis was freely used. The employment of analytical methods spread from Cambridge over the rest of Britain, and by 1830 those methods have come into general use there. End of section 32. Recording by Paul King, Mississauga, Ontario. http pjk.scripts.mit.edu/pkj. Chapter 19, Part 1 of a short account of the history of mathematics by W. W. Rouse. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse. Chapter 19, Mathematicians of Recent Times. It is evidently impossible for me to discuss adequately the mathematicians of the age in which we live, especially as I purposefully exclude from this work and any detailed reference to living writers. I make therefore no attempt to give a complete history of this period, but as a sort of appendix to the preceding chapters I add a few notes on some of the more striking features in the history during this century of pure mathematics, in which I include theoretical dynamics and astronomy. But except for a few allusions, I shall not discuss the applications of mathematics to physics. These notes are brief, and in many cases consist merely of a list of the names of some of those to whom the development of any branch of the subject is chiefly due, and an indication of that part of it to which they have directed most attention.
I would refer anyone who wishes for more details to the invaluable catalogue which has been compiled by the Royal Society of London, and which contains a list under the names of the authors of all the scientific papers contributed during this century to journals and learned societies. In only a few cases do I add any account of the life and works of the mathematicians mentioned. Even with these limitations, it has been very difficult to put together a connected account of the mathematicians of recent times, and I wish to repeat explicitly that I do not suggest, nor do I wish my readers to suppose, that my notes on a subject give the names of all the chief writers who have studied it. In fact, the quality of matter produced has been so enormous that no one can expect to do more than make himself acquainted with the work in some small department. As an illustration of this remark, I must say that I have reason to believe that something like 15,000 separate scientific memoirs are now published every year by the different societies and journals of Europe and America. Most of the treatises on the history of mathematics omit all references to the work produced during this century. The chief exceptions which I am acquainted are a short dissertation by H. Hankel entitled Die Entwicklung der Mathematik in den letzten Jahrhunderten in Tübingen, 1885, the 11th and 12th volumes of Marie's Histoire des Sciences, in which there are notes on mathematicians who were born in the last century, Gerhardt's Geschichte der Mathematik in Deutschland, published in Munich, 1877, and a discours on the professors at the Sorbonne by Hermite in the Bulletin des Sciences Mathématiques in 1890, pages 6 to 36. A few histories of the development of a particular subjects have been written, such as those by the late Isaac Todd Hunter on the theories of attraction and the calculus of probabilities, while annual volumes of the British Association contain a number of reports on the progress in several different branches of modern mathematics. A few similar reports, and notably one in 1857 by J. Bertrand on the development of mathematical analysis, have been presented by the French Academy. I have found these authorities and these reports useful, but I have derived most assistance in writing this chapter from the obituary notices in the proceedings of various learned societies, foreign as well as British. I am also indebted to information kindly furnished me by various friends, and if I do not further dwell on this, it is only that I would not seem to make them responsible for errors and omissions which they would have avoided in their own works. A period of exceptional intellectual activity in any subject is usually followed by one of comparative stagnation, and after the deaths of Lagrange, Laplace, Legendre, and Poisson of the French school, which had occupied so prominent a position at the beginning of this century, ceased for some years to produce much new work. Some of the mathematicians whom I intend first to mention, Gauss, Abel, and Jacobi, were contemporaries of the later years of the French mathematicians just named, but their writings appear to me to belong to a different school, and thus are properly placed at the beginning of a fresh chapter. There is no mathematician of this century whose writings have had a greater effect than those of Gauss. Nor is it on only one branch of the science that his influence has left a permanent mark. I cannot therefore commence my account of the mathematicians of recent times better than by describing very briefly his more important researches. Gauss. Carl Friedrich Gauss, born at Brunswick on April 23, 1777, and died in Göttingen on February 23, 1855. His father was a bricklayer, and Gauss was indebted for liberal education, much against the will of his parents, who wished to profit by his wages as a labourer, to the notice which his talents procured from the reigning duke. In 1792 he was sent to the Caroline College, and by 1795 professors and pupils alike admitted that he knew all of the former could teach him. It was while there that he investigated the method of least squares, and proved by induction the law of quadratic reciprocity. Thence he went to Göttingen, where he studied under Kastner. Many of his discoveries in the theory of numbers were made while a student there. In 1798 he returned to Brunswick, where he earned a somewhat precarious livelihood by private tuition. In 1799 Gauss published his demonstration that every algebraical equation has a root of the form a plus bi, a theorem of which altogether he gave three distinct proofs. In 1801 this was followed by Disquisitiones Arithmeticae, which is printed as the first volume of his collected works. The greater part of it has been sent to the French Academy in the preceding year, and has been rejected with a sneer, which, even if the book had been as worthless as the referees believed, would have been unjustifiable. Gauss was deeply hurt, and his reluctance to publish his investigations may be partly attributable to this unfortunate incident. The next discovery Gauss was in a totally different department of mathematics. The absence of any planet in the space between Mars and Jupiter, where Bode's law would have led observers to expect one, had been long remarked, but it was not until 1801 that any one of the numerous group of minor planets which occupy that space was observed. The discovery was made by Piazzi of Palermo, and was the more interesting as its announcement occurred simultaneously with a publication by Hegel in which he severely criticized astronomers for not paying more attention to philosophy, a science, said he, which would not at once have shewn them that there could not possibly be more than 7 planets, a study of which would therefore have prevented an absurd waste of time in looking for what in the nature of things could never be found. The new planet was named Ceres, but it was seen under conditions which appeared to render it almost impossible to forecast its orbit. The observations were fortunately communicated to Gauss. He calculated its elements, and his analysis proved to him to be the first of theoretical astronomers no less than the greatest of arithmeticians. The attention excited by these investigations procured him in 1807 the offer of a chair at St. Petersburg, which he declined. In the same year he was appointed director to Göttingen Observatory and professor of astronomy there. These offices he retained to his death, and after his appointment he never slept away from his observatory except on one occasion where he attended a scientific conference at Berlin. His lectures were singularly lucid and perfect in form, and it is said that he used here to give the analysis by which he had arrived at his various results, and which it is so conspicuously absent from his published demonstrations, but for fear his auditors should lose the thread of his discourse, he never willingly permitted them to take notes. I have already mentioned Gauss's publications in 1799, 1801, and 1802. For some years after 1807 his time was almost wholly occupied by work connected with his observatory. In 1809 he published at Hamburg his Theoria Motus Corporum Celestium, a treatise which contributed largely to the improvement of practical astronomy and introduced the principle of curvilinear triangulation, and on the same subject, but connected with observations in general, we have his memoir Theoria Combinatonis Observationum Aerobinus Minimus Obnoxia, with a second part and a supplement. Somewhat later he took up the subjects of geodesy, acting from 1821 to 1848 as scientific advisor to the Danish and Hanoverian governments for the survey then in progress. His papers of 1843 and 1866, Über Gegenstände der hohen Geodäsie, contain his researches on the subject. Gauss's researches on electricity and magnetism date from about the year 1830. His first paper on the theory of magnetism, entitled Intensitas vis magnetica terrestris ad mensuram absolutum revocata, was published in 1833. A few months afterwards he, together with Weber, invented the declination instrument and the bifilar magnetometer, in the same year that they erected at Göttingen a magnetic observatory free from iron, as Humboldt and Arago had previously done on a smaller scale. where they made magnetic observations and in particular shewed that it was possible and predictable to send telegraph signals. In connection with this observatory, Gauss founded the association called the Magnetische Verein with the object of securing continuous observations at fixed times. The volumes of their publications Resultate aus der Beobachtungen des magnetischen Vereins for 1838 and 1839 contain two important memoirs by Gauss, one on the general theory of earth magnetism and on the other on the theory of forces attracting according to the inverse square of the distance. Like Poisson, he treated the phenomenon in electrostatics as due to attractions and repulsions between imponderable particles. In electrodynamics he arrived in 1835 at a result equivalent to that given by W. E. Weber in 1846, namely that the attraction between two electrified particles E and E', whose distance apart is r, depends on their relative motion and position according to the formula E r to the power of minus 2 multiplied by the quantity 1 plus r umlaut minus 1 half r squared quantity squared times c to the minus 2. Gauss, however, held that no hypothesis was satisfactory which rested on a formula and was not a consequence of a physical conjecture, and as he could not frame a plausible physical conjecture he abandoned the subject. Such conjectures were proposed by Riemann in 1858 and by C. Newman and E. Betti in 1868. But Helmholtz in 1870, 1873, and 1874 shewed that they were untenable. A simpler view which regards all electric and magnetic phenomena as stresses and motions of a material elastic medium have been outlined by Michael Faraday and was elaborated by James Clerk Maxwell. The latter, by the use of generalized coordinates, was able to deduce the consequences, and the agreement with experiment is close. These and other electric theories were classified and critically discussed in a memoir by J. J. Thomson in 1885. Gauss's researches on optics, including systems of lenses, were published in 1840 in his Dioptrische Untersuchungen. From this sketch it will be seen that the ground covered by Gauss's researches was extraordinarily wide. I will now mention very briefly some of his most important discoveries in pure mathematics. His most celebrated work in pure mathematics is De Disquisitiones Arithmeticae, which has proved the starting point for several interesting investigations on the theory of numbers. This treatise and Legendre's Théorie des Nombres remains standard works on the theory of numbers. But, just as in his discussion of elliptic functions, Legendre failed to rise to the conception of a new subject, and confused himself to regarding their theory as a chapter in the integral calculus, so he treated the theory of numbers as a chapter in algebra. Gauss, however, realized that the theory of discrete magnitudes or higher arithmetic was of a different kind from that of continuous magnitudes or algebra, and he introduced a new notation and new methods of analysis of which subsequent writers have generally availed themselves. In particular, the Disquisitiones Arithmeticae introduced the modern theory of congruences of the first and second orders, and to this Gauss reduced intermediate analysis. In it also he discussed the solution of binomial equations of the form x to the power n equals 1. This involves the celebrated theorem that the only regular polygons which can be constructed by elementary geometry are those in which the number of sides is 2 to the power of m multiplied by 2 to the power of n plus 1, where m and n are integers and 2 to the power n plus 1 is a prime, a discovery he had made in 1796. He developed the theory of ternary quadratic forms involving two indeterminates. He also investigated the theory of determinants, and it was on Gauss's results that Jacobi based his researches on that subject. The theory of functions of double periodicity had its origin in the discoveries of Abel and Jacobi, which I describe later. Both these mathematicians arrived at the theta functions which play so large a part in the theory of the subject. Gauss, however, had independently, and indeed at a far earlier date, discovered these functions and their chief properties, having been led to them by certain integrals which occurred in the determinatio attractionis, to evaluate which he invented the transformation now associated with the name of Jacobi. Though Gauss at a later time communicated the fact to Jacobi, he did not publish his researches. They occur in a series of notebooks of a date not later than 1808 and are included in his collected works. Of the remaining memoirs in pure mathematics, the most remarkable are those on the theory of biquadratic residues, wherein the notion of complex numbers of the form a plus bi was first introduced into the theory of numbers, in which are included several tables, and notably one of the number of the classes of binary quadratic forms, that of relating to the proof of the theorem at every numerical equation has a real or imaginary root, that on the summation of series, that on the hypergeometric series, which contains a discussion of the gamma function, and lastly one on interpolation. His introduction of rigorous tests for the convergency of infinite series is especially noticeable. Finally, we have the important memoir on the conformal representation of one surface upon another, in which the results given by Lagrange for surfaces of revolution are generalized for any surfaces. In the theory of attractions, we have a paper on the attraction of homogeneous ellipsoids. The already mentioned memoir of 1839, Allgemeine Lesssatz in Beziehung auf die inverkehrten Verhältnis des Quadrats der Entfernung, on the theory of forces attracting according to the inverse square of the distance, and the memoir Determinatio Attractionis, in which it is shewn that the secular variations which the elements of the orbit of a planet experience from the attraction of another planet which disturbs it are the same as if the mass of the disturbing planet were distributed over its orbit into an elliptic ring in such a manner that equal masses of the ring would correspond to the arcs of the orbit described in equal times. The great masters of modern analysis are Lagrange, Laplace, and Gauss, who were contemporaries. It is interesting to note the marked contrast in their styles. Lagrange is perfect both in form and matter. He is careful to explain his procedure, and though his arguments are general, they are easy to follow. Laplace, on the other hand, explains nothing, is absolutely indifferent to style, and if satisfied with that his results are correct, is content to leave them either with no proof or with a faulty one. Gauss is as exact and elegant as Lagrange, but even more difficult to follow than Laplace, for he removes every trace of the analysis by which he reached his results, and studies to give a proof which, while rigorous, shall be as concise and synthetical as possible. End of part 34. Recording by Paul King, Mississauga. http pjk.scripts.mit.edu/pkj. Chapter 19, Part 2 of a short account of the history of mathematics by W. Rouse. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics by W. Rouse. Chapter 19, Mathematics of Recent Times, Part 2. Dirichlet. One of Gauss's pupils to whom I may here allude is Lejeune Dirichlet, who is generally known for his exposition of the discoveries of Jacobi, who was his father-in-law, and of Gauss, rather than for his own original investigations, valuable though some of these are. Peter Gustave Lejeune Dirichlet was born at Rennes on February 13, 1805, and died at Göttingen on May 5, 1859. He held successively professorships at Breslau and Berlin, and on Gauss's death in 1855 was appointed to succeed him as professor of the higher mathematics at Göttingen.
He intended to finish Gauss's incomplete works, for which he was admirably fitted, but his early death prevented this. He produced, however, several memoirs which have considerably facilitated the comprehension of some of Gauss's more abstruse methods. Of Diraclet's original work, the most celebrated is that on the determination of means with applications to the distribution of prime numbers. The researches of Gauss on the theory of numbers were continued or supplemented by Jacobi, who first proved the law of cubic reciprocity, discussed on the theory of residues, and in his Canon Arithmeticus gave a table of residues of prime roots. Eisenstein. This subject was next taken up by Ferdinand Gotthold Eisenstein, a professor at the University of Berlin, who was born at Berlin on April 16, 1823, and died there on October 11, 1852. The theory of numbers may be divided into two main divisions, namely, the theory of congruences and the theory of forms. The solution of the problem of the representation of numbers by binary quadratic forms is one of the great achievements of Gauss, and the fundamental principles upon which the treatment of such questions rest were given by him in the Disquisitiones Arithmeticae. Gauss there added some results relating to ternary quadratic forms, but the general extension from 2 to 3 indeterminates was the work of Eisenstein, who in his memoir Neue Theorem der höheren Arithmetik defined the ordinal and generic characters of ternary quadratic forms of an uneven determinant, and in the case of definite forms assigned the weight of any order or genus, but he did not consider forms of an even determinant, nor give any demonstration of his work. Eisenstein also considered the theorems relating to the possibility of representing a number as a sum of squares, and shewed that the general theorem was limited to 8 squares. The solutions in the cases of 2, 4, and 6 squares may be obtained by means of elliptic functions, but the cases in which the numbers of squares is uneven involve the special processes peculiar to the theory of numbers. Eisenstein gave the solution in the case of 3 squares. He also left a statement of the solution he had obtained in the case of 5 squares, but his results were published without proofs and apply only to numbers which are not divisible by a square. Among Eisenstein's other investigations I single out for special mention the remarkable rule he enunciated by means of which it is possible to distinguish whether a given series represents an algebraical or transcendental function. Henry Smith. One of the most original and powerful mathematicians of the school founded by Gauss was Henry Smith. Henry John Stephen Smith was born in London on November 2, 1826, and died at Oxford on February 9, 1883. He was educated at Rugby and at Balliol College, Oxford, of which latter society he was a fellow, and in 1861 he was elected Savilian Professor of Geometry at Oxford, where he resided till his death. The subject in connection with which Smith's name will be always specially remembered is the theory of numbers, and to this he devoted the years from 1854 to 1864. The results of his historical researches were given in his report published in parts in the Transactions of the British Association from 1859 to 1865. This report contains an account of what had been done on the subject to that time, together with some additional matter. The chief outcome of his own original work on the subjects is included in 2 memoirs printed in the Philosophical Transactions for 1861 and 1867, the first being on linear indeterminate equations and congruences, and the second on the orders and genera of ternary quadratic forms. In the latter memoir, demonstrations of Eisenstein's results and their extension to ternary quadratic forms of an even determinant were supplied, and a complete classification of ternary quadratic forms was given. Smith, however, did not confine himself to the case of 3 indeterminates, but succeeded in establishing the principles on which the extension to to the general case of n indeterminates depends, and obtained the general formulae, thus effecting the greatest advance made in the subject since the publication of Gauss's work. In the account of his methods and results which appeared in the Proceedings of the Royal Society, Smith remarked that the theorems relating to the representation of numbers by four squares and other simple quadratic forms are deducible by a uniform method from the principles there indicated, as also are the theorems relating to the representation of numbers by 6 and 8 squares. He then proceeded to say that as the series of theorems relating to the representation of numbers by sums of squares ceases, for the reason assigned by Eisenstein, when the number of squares surpasses 8, it was desirable to complete it. The results for even squares were known. The principal theorems relating to the case of 5 squares had been given by Eisenstein, but he had considered only those numbers which are not divisible by a square, and he had not considered the case of 7 squares. Smith here completed the enunciation of the theorems for the case of 5 squares, and added the corresponding theorems for the case of 7 squares. This paper was the occasion of a dramatic incident in the history of mathematics. 14 years later, in ignorance of Smith's work, the demonstration and completion of Eisenstein's theorems for 5 squares were set by the French Academy as a subject of their Grand Prix des Sciences Mathématiques. Smith wrote out the demonstration of his general theorems so far as was required to prove the results in the special case of 5 squares, and only a month after his death in March 1883 the prize was awarded to him, another prize being awarded to H. Minkowski of Bonn. No episode could bring out in a more striking light the extent of Smith's researches than that a question of which he had given in the solution in 1867 as a corollary from the general formulae which governed the whole class of investigations to which it belonged, should have been regarded by the French Academy as one whose solution which is of such difficulty and importance as to be worthy of their great prize. It has also been a matter of comment that they should have known so little of contemporary English and German researches on the subject as to be unaware that the result of the problem they were proposing was then lying in their own library. Among Smith's other investigations I may specially mention his geometrical memoir Sur calcul problème cubique et biquadratique, for which in 1868 he was awarded the Steiner Prize of the Berlin Academy. In a paper which he contributed to the Atti of the Accademia dei Lincei for 1877, he established a very remarkable analytical relation connecting the modular equation of order n and the theory of binary quadratic forms belonging to the positive determinant n. In this paper, the modular curve is represented analytically by a curve in such a manner as to present an actual geometrical image of the complete systems of the reduced quadratic forms belonging to the determinant, and a geometrical interpretation is given to the ideas of class, equivalence, and reduced form. He was also the author of important papers in which he succeeded in extending to complex quadratic forms many of Gauss's investigations relating to real quadratic forms. He was led by researches on the theory of numbers to the theory of elliptic functions, and the results he arrived at, especially on the theory of the theta and omega functions, are of importance. The theory of numbers as treated today may be said to originate with Gauss. I have already mentioned very briefly the subject of the subsequent investigations of Jacobi, Dirichlet, Eisenstein, and Henry Smith. Among other mathematicians who have written on it I may allude to the following: Riemann, who investigated the distribution of primes; James Joseph Sylvester, Savilian professor in the University of Oxford, born in London on September 3, 1814, who has also written on the distribution of primes; Cauchy, who in particular discussed the expression of quadratic binomials; Joseph Liouville, the editor from 1836 to 1874 of the well-known journal, who was born at Saint Omer on March 24, 1809, and died in 1882, most of whose numerous investigations dealt with the representation of numbers by special forms. Ernest Edward Kummer, born at Soreau on January 29, 1810, and until recently professor at Berlin, to whom we owe the conception of the so-called ideal primes, which are required in the treatment of complexes, and which he applied to the problem of Fermat's equation, and whose paper on hypergeometric series may rank with that by Gauss as a classical memoir on the subject. Leopold Kronecker, professor in Berlin, born at Liegnitz on December 7, 1823, and died at Berlin on December 29, 1891, most of whose investigations on this branch of mathematics were on ternary and quadratic forms. On his investigations generally see the Bulletin of the New York Mathematical Society, Volume 1, pages 173 to 184. See also below, page 469. Charles Hermite, professor in Paris, born in Lorraine on December 24, 1822, who wrote on ternary forms. Julius Wilhelm Richard Dedekind, born at Brunswick on October 6, 1831, whose more important researches given in an appendix to his edition of Dirichlet's writings are on ideal primes. See also below, page 493. Panutij Chebyshev, formerly professor at the University of St. Petersburg, born in Russia in 1821, who has written on the number of primes between given limits, a problem also considered by Legendre, Dirichlet, and Riemann. And James Whitebread Lee Glacier, a fellow and tutor of Trinity College in Cambridge, born at Lewisham on November 5, 1848, from whose numerous papers I may single out those relating to prime numbers, those on functions of a number which are formed from its real or complex divisors, and on those on the possible divisors of numbers of a given form. Finally, I may mention that the problem of the partition of numbers, to which Euler paid considerable attention, has in recent times attracted the attention of Arthur Cayley, Sadlerian professor in the University of Cambridge, born in Richmond, Surrey, on August 16, 1821, of Sylvester, and of Percy Alexander MacMahon, professor at Woolwich, and a major in the English artillery, born at Malta on September 26, 1854. Interest in problems connected with the theory of numbers seems recently to have flagged, and possibly it may be found hereafter that the subject is approached better on other lines. The theory of functions of double and multiple periodicity is another subject to which much attention has been paid during this century. I have already mentioned that as early as 1808 Gauss had discovered the theta functions and their chief properties, but his investigations remained for many years concealed in notebooks, and it was to the researches made between 1820 and 1830 by Abel and Jacobi that the modern development of the subject is due. The treatment of it has been completely superseded that used by Legendre, and they are justly reckoned as the creators of this branch of mathematics. Abel. Niels Henrik Abel, born at Findo in Norway on August 5, 1802, and died at Arendal on April 6, 1829, at the age of 26. His memoirs on elliptic functions, which were originally published in Krell's journal, treat the subject from the point of view of the theory of equations and algebraic forms, a treatment to which his researches naturally led him. The important and very general result known as Abel's theorem, which was subsequently applied by Riemann to the theory of transcendental functions, was sent to the French Academy in 1828, but, mainly through the action of Cauchy, was not published for several years. The name of Abelian function has been given to the higher transcendents of multiple periodicity, which were first discussed by Abel. He criticized the use of infinite series, but I do not know that the results lead to any definite rules for testing convergency. As illustrating his fertility of ideas, I may in passing notice his celebrated demonstration that it is impossible to solve a quintic equation by means of radicals. This theorem was the more important since it definitely limited a field of mathematics which had previously attracted numerous writers. I should add that this theorem had been enunciated as early as 1798 by Paolo Ruffini, an Italian physician practicing at Modena, but I believe that the proof he gave was deficient in generality. Jacobi. Carl Gustav Jacob Jacobi, born of Jewish parents at Potsdam on December 10, 1804, and died at Berlin on February 18, 1851, was educated at the University of Berlin, where he obtained the degree of Doctor of Philosophy in 1825. In 1827, he became extraordinary professor of mathematics at Königsberg, and in 1829 was promoted to be an ordinary professor. This chair he occupied till 1842, when the Prussian government gave him a pension, and he moved to Berlin, where he continued to live until his death in 1851. Jacobi's most celebrated investigations are those on elliptic functions, the modern notation in which is due to him, and the theory of which he established simultaneously with Abel, but independently of him. These are given in his treatise Fundamenta Nova Theoreae Functionum Ellipticarum, Königsberg, 1829, and in some later papers in Krell's journal. The correspondence between Legendre and Jacobi on elliptic functions has been reprinted in the first volume of Jacobi's collected works. Jacobi, like Abel, recognized that elliptic functions were not merely a group of theorems on integration, but that they were types of a new kind of function, namely one of double periodicity. Hence he paid particular attention to the theory of the theta function. The following passage in which he explains this view is sufficiently interesting to deserve textual reproduction. Equo cum universam que fingi potest, amplicatur periodaticatam analyticam elucet, functiones ellipticas non alis ad numerari deber transcendentibus, que quibusdem godent elegantis fortas pluribus, illas aut maioribus, sed speciem quadnam is ines perfecti et absoluti. Among Jacobi's other investigations, I may specially single out his papers on determinants, which did a great deal to bring them into general use, and particularly his invention of the Jacobian, that is, of the functional determinant formed by the n-squared partial differential coefficients of the first order of n, given functions of n independent variables. I ought also to mention his papers on abelian transcendents, his investigations on the theory of numbers, his important work on the theory of partial differential equations, his development of the calculus of variations, and his numerous memoirs on the planetary theory and other particular dynamical problems, in the course of which he also extended the theory of differential equations. Most of the results of the researches last named are included in his Vorlesungen über Dynamik, edited by Klebsch, Berlin, 1866. Riemann. Georg Friedrich Bernhard Riemann was born at Bersens on September 17, 1826, and died at Selaska on July 20, 1866. He studied at Göttingen under Gauss, and subsequently at Berlin under Jacobi, Dirichlet, Steiner, and Eisenstein, all of whom were professors there at the same time. His earliest paper, written in 1850, was on algebraic functions of a complex variable, and on it the recent investigations of Schwarz, Klein, and Poincaré are largely based. To those I refer very briefly below. In 1854, Riemann wrote his celebrated memoir on the hypotheses on which geometry is founded. This was succeeded by his memoirs on elliptic functions and the theory of numbers. He also wrote on physical subjects. The question of the truth of the assumptions usually made in our geometry had been considered by J. Sacheri as long ago as 1733, and in more recent times had been discussed by Nikolai Ivanovich Lobachevsky, professor at Caen, born at Nizhny Novgorod in 1793 and died at Kazan on February 12, 1856, in 1826 and again in 1840. By Gauss in 1831 and in 1846, and by Johann Bolyai, born at Klausenburg in 1802 and died at Maros Vasarhelyi in 1860 and in 1832 in the appendix to the first volume of his father's Tentamen, but Riemann's memoir of 1854 attracted general attention to the subject of hypergeometry, and the theory has been since extended and simplified by various writers, notably by Eugenio Beltrami, professor at Pavia, born at Cremona in 1835, and by Hermann Ludwig Ferdinand von Helmholtz, professor at Berlin, born at Potsdam on August 31, 1821. The subject is so technical that I confine myself to a bare sketch of the argument from which the idea is derived. That a space of two dimensions should have the geometrical properties with which we are made familiar in the study of elementary geometry, it is necessary that it should be possible at any place to construct a figure congruent to a given figure, and this is so only if the product of the principal radii of curvature at every point in space or surface be a constant. There are three species of surfaces which possess this property, namely 1. Spherical surfaces where the product is positive, 2. Plane surfaces which led to Euclidean geometry where it is 0, and 3. What Beltrami has called pseudospherical surfaces where it is negative. Moreover, if any surface be bent without dilation or contraction, the measure of curvature remains unaltered. Thus these three species of surfaces are types of three kinds on which congruent figures can be constructed. For instance, a plane can be rolled into a cone, and the system of geometry on a conical surface is similar to that on a plane. These kinds of space of two dimensions are distinguished from one another by a simple test. Through a point of spherical space, no geodetic line, a geodetic line being defined as the shortest distance between 2 points, can be drawn parallel to a given geodetic line. Through a point of Euclidean or plane space, one and only one geodetic line, i.e. a straight line, can be drawn parallel to a given geodetic line. Through a point of pseudospherical space, more than one geodetic line can be drawn parallel to a given geodetic line, but all these lines form a pencil whose vertical angle is constant. It may be thought that we have a demonstration that our space is plane, since through a given point we can draw only one straight line parallel to a given straight line. This is not so, for it is conceivable that our means of observation do not permit us to say with absolute accuracy whether two lines are parallel. Hence, we cannot use this as a means to tell whether our space is plane or not. A better test can be deduced from the proposition that in any two-dimensional space of uniform curvature, the sum of the angles of a triangle, if it differ from two right angles, will differ by a quantity proportional to the area of the triangle. Hence it may happen possibly that although for triangles such as we can measure, the difference is imperceptible, yet for triangles which are millions of times bigger, there would be a sensible difference. If space be spherical or pseudospherical, its extent is finite. If it be plane, its extent is infinite. In regard to pseudospherical space, I should add that its extent may be infinite if it be constructed in space of 4 dimensions. In the preceding sketch of the foundations of non-Euclidean geometry, I have assumed tacitly that the measure of a distance remains the same everywhere. Klein has shown that if this be not the case, and if the law of the measurement of distance be properly chosen, we can obtain 3 systems of plane geometry analogous to the 3 systems mentioned above. These are called respectively elliptic, parabolic, and hyperbolic geometries. The above refers only to hyperspace of two dimensions. Naturally, there arises the question whether there are different kinds of hyperspace of three or more dimensions. Riemann showed that there are three kinds of hyperspace of three dimensions having properties analogous to the three kinds of hyperspace of two dimensions already discussed. These are differentiated by the test whether at every point no geodetical surfaces or one geodetical surface or a fasciculus of geodetical surfaces can be drawn parallel to a given surface, a geodetical surface being defined as such that every geodetic line joining two points on it lies wholly on the surface. I return now to Riemann's other investigations. In multiply periodic functions, it is hardly too much to say that he in his memoir in Bouchart's journal for 1857 did for the abelian functions what Abel had done for the elliptic functions, and it is this perhaps that will constitute one of his chief claims to future distinction. In the theory of numbers, Riemann's short tract of 8 pages on the number of primes which lie between two given numbers affords a striking instance of his analytical powers. Legendre had previously shewn that the number of primes less than n is very approximately n divided by the quantity log n minus 1.08366. But Riemann went further, and this tract and a memoir by Chebyshev contains nearly all that had been done, yet in connection with a problem of so obvious of a character that it has suggested itself to all who has considered the theory of numbers, and yet which overtax the powers even of Lagrange and Gauss. Among others than those already named, I may mention the following who have written on elliptic and abelian functions. Johann Georg Rosenhain, professor in Königsberg, born there on June 10, 1816, and died in 1887, who wrote in 1884 on the hyperelliptic double theta function and functions of two variables with 4 periods. Adolf Goepel, born at Rostock in September 1812 and died at Berlin in March 1847, who discussed hyperelliptic functions. See Krell's Journal, volume 35, 1847, pages 313 to 318. Karl Weierstrass, professor in Berlin, born at Ostenfeld on October 31, 1815, whose earlier researches related to the theta functions which he treated under a modified form in which they are expressible in powers of the modulus. At a later period he developed a method for treating all elliptic functions in a symmetrical manner, a process to which he was naturally led by his researches on the general theory of functions. In this theory, the theta functions are independent of the form of their space boundaries. Leopold Kronecker, who wrote on elliptic functions. Francesco Brioschi of Rome, who wrote on elliptic and hyperelliptic functions. Henry Smith, who discussed the transformation theory, the theta and omega functions, and certain functions of the modulus. Cayley, who was the first to work out in 1845 the theory of doubly infinite products and determine their periodicity, and who has written at length on the connection between the researches of Legendre and Jacobi. His later writings have dealt mainly with the theory of transformations and the modular equation. Cayley's collected works are now being issued by the University of Cambridge. The researches of Hermite are mostly concerned with the transformation theory, the higher development of the theta functions, and the connection between the methods and results of Weierstrass and Jacobi. The transformation of the double theta function has been also considered by Leo Königsberger, professor at Heidelberg, born in Prussia 1837. See his lectures published at Leipzig in 1874. The investigations of George Henri Haffan, an officer in the French army, born at Rouen on October 30, 1844, and died in Paris on May 21st, 1889, are largely founded on Weierstrass's work. A sketch of Helfen's life and works given in Liouville's journal for 1889, pages 345 to 359, and in the Comptes Rendus, 1890, volume 110, pages 489 to 497. See also below, pages 481 to 482. Felix Christian Klein, born in 1849, now professor in Göttingen, has written on abelian functions, elliptic, modular functions, and hyperelliptic functions. Finally, H. A. Schwarz, formerly of Göttingen, now in Berlin, born 1845. H. W. Weber of Marburg, M. Nother of Erlangen, W. Stahl of Aix-la-Chapelle, F. G. Frobenius, now of Berlin and formerly of Zurich, and Glaisher have written on various branches of the theory, and Dr. Glaisher has in particular developed the theory of the zeta function. The textbook by Briot and Bouquet contains a clear account of the elliptic functions as it exists at present, developed from the point of view of the complex variable. Albert Briot was born at Saint Hippolyte in 1817, occupied a chair at the Sorbonne in Paris, and died in 1882. Jean-Claude Bouquet was born in 1819 and died in Paris in 1885. End of section 35 of A Short Account of the History of Mathematics by W. W. Rouseball. Recording by Paul King, Mississauga, Ontario. pjk.scripts.mit.edu/PKJ. Chapter 19, Part 3 of A Short Account of the History of Mathematics by W. W. Rouseball. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu. A Short Account of the History of Mathematics by W. W. Rouseball. Chapter 19. Mathematics of Recent Times, Part 3. The consideration of algebraical, trigonometrical, elliptic, hyperelliptic, and other special kinds of functions paved the way for a theory of functions, which promises to prove a most important and far-reaching branch of mathematics. To a large extent, this is the work of living mathematicians, and therefore outside the limits of this chapter. I will content myself by referring to the following writers. First, I may mention Cauchy, who gave the general elementary theory of functions, and Liouville, who wrote chiefly on doubly periodic functions. Their investigations were extended and connected in the work of Briot and Bouquet, and further been developed by Hermite. Next, I may refer to the researches on the theory of algebraic functions which have their origin in Riemann's paper of 1850. Schwarz has established accurately certain theorems of which proofs given by Riemann were open to objection. Klein has connected Riemann's theory of functions with the theory of groups and have written on automorphic functions. Henri Poincaré, professor in Paris, born at Nancy in 1854, has also written on automorphic functions and on the general theory with special applications to differential equations. Finally, I may refer to the work of Weierstrass and Mittag-Leffler. Of these, Karl Weierstrass has created a large part of the modern theory of functions, and in particular has constructed the theory of uniform analytical functions. And Magnus Gustav Mittag-Leffler, born at Stockholm in 1846 and now professor there, has greatly developed the theory of analytical functions, a subject on which Hermite has also written. In connection with these researches, Paul-Émile Appel, professor in Paris, born at Strasbourg in 1858, C. Émile Picard of Paris, Edouard Goursat of Paris has written on special branches of the theory. As textbooks, I may mention Dr. Forsyth's Theory of Functions of a Complex Variable, Cambridge, 1893, and Carl Neumann's Vorlesungen über Riemanns Theorie der Absälischen Integral, 2nd edition, Leipzig, 1884. The theory of numbers may be considered as a higher arithmetic, and the theory of elliptical and abelian functions as a higher trigonometry. The theory of higher algebra, including the theory of equations, has also attracted considerable attention, and was a favourite subject of study of the three mathematicians, Cauchy, Hamilton, and De Morgan, whom I propose to mention next, though the interests of these writers were by no means limited to this subject. Cauchy. The first of these mathematicians is the best representative of the French school of analysis in this century. Augustin Louis Cauchy, who was born in Paris on August 21st, 1789, and died at Sceaux on May 25th, 1857, was educated at the Polytechnic School, the nursery of so many French mathematicians of that time, and adopted the profession of a civil engineer. His earliest mathematical paper was one on polyhedra in 1811. Legendre thought so highly of it that he asked Cauchy to attempt the solution of an analogous problem which had baffled previous investigators, and his advice was justified by the success of Cauchy in 1812. Memoirs on analysis and the theory of numbers presented in 1813, 1814, and 1815 shewed that his ability was not confined to geometry alone. In one of these papers he generalized some results which had been established by Gauss and Legendre. In another of them he gave a theorem on the number of values which an algebraical function can assume when the literal constants it contains are interchanged. It was the latter theorem that enabled Abel to shew that in general an algebraic equation of a degree higher than the fourth cannot be solved by the use of purely algebraical expressions. To Cauchy and Gauss we owe the scientific treatment of series which have an infinite number of terms, and the former established general rules for investigating the convergency and divergency of such series. It is only a few works of an earlier date that contain any discussion as to the limitations of the series employed. It is said that Laplace, who was present when Cauchy read his first paper on the subject, was so impressed by the illustrations of the danger of employing such series without a rigorous investigation of their convergency that he put on one side the work on which he was then engaged and denied himself to all visitors, in order to see if any of the demonstrations given in the earlier volumes of the Mécanique Céleste were invalid. And he was fortunate enough to find that no material errors had been thus introduced. The treatment of series and of the fundamental conceptions of the calculus in most of the textbooks then current was based on Euler's works, and to any one trained to accurate habits of thought was not free from objection. It is one of the chief merits of Cauchy that he placed those subjects on a logical foundation. On the Restoration in 1816 the French Academy was purged, and, in spite of the indignation and scorn of French scientific society, Cauchy accepted a seat which was procured for him by the expulsion of Monge. He was also at the same time made professor at the Polytechnic, and his lectures there on algebraic analysis, the calculus, and the theory of curves were published as textbooks. On the Revolution in 1830 he went into exile and was first appointed professor at Turin, where he soon moved to Prague to undertake the education of the Comte de Chambord. He returned to France in 1837 and in 1848 and again in 1851 by special dispensation of the emperor was allowed to occupy a chair of mathematics without taking the oath of allegiance. His activity was prodigious, and from 1830 to 1859 he published in the Transactions of the Academy of the Comtes Rendus over 600 original memoirs and about 150 reports. In most of them the feverish haste with which they were thrown off is too visible, and many are marred by obscurity, repetition of old results, and blunders. Among the more important of his researches are the discussion of tests for the convergency of series, and the determination of the number of real and imaginary roots of any algebraic equation. His method of calculating these roots approximately, his theory of the symmetric functions of the coefficients of equations of any degree, his a priori evaluation of quantity less than the least difference between the roots of an equation, and his papers on determinants in 1841, which did a great deal to bring them into general use. Cauchy also did something to reduce the art of determining definite integrals to a science, but this branch of the integral calculus still remains without much system or method. The rule for finding the principal values of integrals was enunciated by him, and the calculus of residues was his invention. His proof of Taylor's theorem seems to have originated from a discussion of the double periodicity of elliptic functions. The means of shewing a connection between the different branches of a subject by giving imaginary values to independent variables is largely due to him. He also gives a direct analytical method for determining planetary inequalities of long period, and to physics he contributed a memoir on the quantity of light reflected from the surfaces of metals, as well as other papers on optics. Argand. I may mention here the name of Jean-Robert Argand, who was born at Geneva on July 22, 1768, and died circa 1825. In his essay, issued in 1806, he gave a geometrical representation of a complex number, and applied it to shew that every algebraic equation has a root. This was prior to the memoirs of Gauss and Cauchy on the same subject. But the essay did not attract much attention when it was first published. An earlier demonstration that the square root of -1 indicates perpendicularity due to Buet was published in the Philosophical Transactions for 1806, and the idea was foreshadowed in a memoir by H. Kuhn in the Transactions for 1750 of the St. Petersburg Academy. Hamilton. In the opinion of some writers, the theory of quaternions will be ultimately esteemed by one of the great discoveries of this century. The discovery is due to Sir William Rowan Hamilton, who was born of Scotch parents in Dublin on August 4, 1805, and died there on September 2, 1865. His education, which was carried out at home, seems to have been singularly discursive. Under the influence of an uncle who was a good linguist, he first devoted himself to linguistic studies. By the time he was 7 he could read Latin, Greek, French, and German with facility, and when 13 he was able to boast that he was familiar with as many languages as he had lived years. It was about this time that he came across a copy of Newton's Universal Arithmetic. This was his introduction to modern analysis, and he soon mastered the elements of analytical geometry and the calculus. He next read the Principia, and the 4 volumes then published of Laplace's Mécanique Céleste. In the latter he detected a mistake, and his paper on the subject, written in 1823, placed him at once in the front rank of mathematicians. In the following year he entered at Trinity College, Dublin. His university career is unique, for the chair of astronomy becoming vacant in 1827, while he was yet an undergraduate, he was asked by the electors to stand for it, and was elected unanimously, it being understood that he should be left free to pursue his own line of study. His earliest paper, written in 1823, was on optics, and was published in 1828 under the title of A Theory of Systems of Rays, which 2 supplements, written in 1831 and 1832, were afterwards added. In the latter of these the phenomenon of conical refraction is predicted. This was followed by a paper in 1827 on the principle of varying action, and in 1834 and 1835 by memoirs on a general method in dynamics, the subject of theoretical dynamics being properly treated as a branch of pure mathematics. His lectures on quaternions was published in 1852. Amongst his other papers I may specially mention one on the form of the solution of the general algebraic equation of the fifth degree, which confirmed the conclusion arrived at by Abel that it cannot be expressed in terms of the more elementary operations and functions. One on fluctuating functions, one on the hodograph, and lastly on the numerical solution of differential equations. His Elements of Quaternions were issued in 1866. Of this, a competent authority says that the methods of analysis there given shew as great an advance over those of analytical geometry as the latter shewed over those of Euclidean geometry. In more recent times the subject has been further developed by Tate. Hamilton was painfully fastidious on what he published, and he left an immense collection of manuscript books which are now in the library of Trinity College Dublin, and some of which it is hoped will be ultimately printed. Grassmann. The idea of non-commutative algebras and of quaternions seemed to have occurred to Grassmann about the same time as to Hamilton. Hermann Gunther Grassmann, born at Stettin on April 15, 1809, and died there in 1877. He was a professor at the gymnasium at Stettin. His researches on non-commutative algebras are contained in his Ausdehnungslehre, first published in 1844 and enlarged in 1862. The scientific treatment of the fundamental principles of algebra initiated by Hamilton and Grassmann were continued by De Morgan and Boole, and subsequently was further developed by H. Hankel in his work on complexes, 1867, and by G. Cantor on his memoirs on the theory of irrationals, 1871. The discussion is however so technical that I am unable to do more than allude to it. Grassmann also investigated the properties of homoalloidal hyperspace. De Morgan. Augustus de Morgan, born in Madura, Madras, in June 1806 and died in London on March 18, 1871, was educated at Trinity College, Cambridge, but in the then state of the law was, as a Unitarian, ineligible to a fellowship. In 1828 he became professor at the newly established University of London, which is the same institution as that now known as University College. There, except for 5 years from 1831 to 1835, he taught continuously till 1867, and through his works and pupils exercised a wide influence on English mathematicians of the present day. The London Mathematical Society was largely his creation, and he took a prominent part in the proceedings of the Royal Astronomical Society. He was perhaps more deeply read in the philosophy and history of mathematics than any of his contemporaries, but the results are given in scattered articles as well, which well deserve collection and republication. A list of these is given in his life, and I have made considerable use of some of them in this book. The best known of his works are the Memoirs of the Foundation of Algebra, Cambridge Philosophical Transactions, volumes 8 and 9, his treatise on the differential calculus published in 1842, a work of great ability and noticeable for the rigorous treatment of infinite series, and his articles on the calculus of functions on the theory of probabilities in the Encyclopaedia Metropolitana. The article on the calculus of functions contains an investigation of the principles of symbolic reasoning, but the applications deal with the solution of functional equations rather than with the general theory of functions. The article on the theory of probabilities gives a clear analysis of the mathematics of the subject to the time at which it was written. Besides those above named, I may mention the following who have written on the subjects of higher algebra, the theory of forms, and the theory of equations. Joseph Ludwig Rabe, who in 1832 discussed the test for the convergency of series, a subject also discussed later by Joseph Louis Francois Bertrand, secretary of the French Academy, born in Paris in 1822, Kummer, Ulysse Dini of Pisa, and A. Pringsheim of Munich. And on the researches of the above writers see the Bulletin of the New York Mathematical Society, October 1892, pages 1 to 10. George Boole, born at Lincoln in November 2nd, 1815, died at Cork on December 8th, 1864, who invented a system of non-commutative algebra and from whose memoirs on linear transformations part of the theory of covariance has developed. Évariste Galois, one of the most original and powerful mathematicians of this century, born at Paris on October 26, 1811, and then killed in a duel on May 30th, 1832, at the early age of 20, whose writings are mainly concerned with the theory of equations and substitution groups. On his investigations, see Liouville's Journal for 1846, volume 11, pages 381 to 444, and the American Journal of Mathematics for 1891, volume 13, pages 109 to 142. Carl Wilhelm Borchardt, professor in Berlin, born there on February 22nd, 1817, died there 1880, who in particular discussed generating functions in the theory of equations and arithmetic geometric means. A collected edition of his works, edited by G. Hettner, was issued at Berlin in 1888. Cayley, whose 10 classical memoirs on quantics, binary and ternary forms, and researches on non-commutative algebras, especially on matrices, will be found in the collected edition of his works. Sylvester. From among those whose numerous memoirs I may in particular single out, those on canonical forms, on the theory of contravariants, reciprocants of differential invariants, on the theory of equations, and that on Newton's rule, to which I may add that he has created the language and notation of considerable parts of the subjects on which he has written. Camille Jordan, who has written on the theory of substitutions in general and with special applications to differential equations. Sir George Gabriel Stokes, Lucasian professor in the University of Cambridge, born near Sligo on August 13, 1819, who has written on the critical values of the sums of the periodic series and on the summation of series. Cambridge Philosophical Transactions, 1847, volume 8, pages 533 to 583. See also below, pages 492 and 496. Eugene Netto of Strasbourg, who has written on substitutions. Hermite, who has in particular discussed the theory of associated contravariants in binary quantics, the theory of ternary quantics, and who has applied elliptic functions to the solution of the quintic equation. Enrico Betti of Pisa, who died in 1892, and Brioschi, both of whom discussed binary quantics. Siegfried Heinrich Ehrenhold, born at Engerberg on July 16, 1819, who developed symbolic methods, especially in connection with ternary quantics. This was done concurrently with, but independently of, Cayley's work on the same subject. Paul Gordin, professor at Erlangen, who had discussed the theory of forms and shewed that there are only a finite number of concomitants of quantics. An edition of his work on invariants, determinants, and binary forms, edited by G. Kersteiner, was issued at Leipzig in 3 volumes, 1885, 1887, and 1893. Rudolf Friedrich Alfred Klebsch, born at Königsberg in 1833, died in Göttingen, where he was professor in 1872, who also independently investigated the theory of binary forms in some papers collected and published in 1871. An account of his life and works is printed in the Mathematische Annalen, 1873, volume 6, pages 197 to 202, and 1874, volume 7, pages 1 to 55. See also below. McMahon, who has written on the connection of symmetric functions, the derivation of invariants and the covariance from elementary algebra, and the concomitants of binary forms. Sophus Lai, professor at Leipzig, who has written on groups of continuous substitutions, differential invariants, and complexes of lines. Klein, who has investigated the problem of discontinuous substitutions in polyhedra groups. And lastly, Andrew Russell Forsyth, Fellow and Lecturer of Trinity College, Cambridge, born at Glasgow on June 18, 1858, who has developed the theory of invariance of differential equations, ternariants and quaternariants. No account of contemporary writings of this subject would be complete without a reference to the admirable textbooks produced by George Salmon, Provost at Trinity College, Dublin, born in 1819, in his Higher Algebra, and by Joseph Alfred Serret, professor at the Sorbonne in Paris on August 30, 1819, died in 1885, in his Cours d'Algèbre Supérieure, in which the chief discoveries of their respective authors are embodied. An admirable historical summary of the theory of the complex variable is given in the Vosolingen über die komplexen Zahlen, Leipzig, 1867, by H. Henkel, professor at Tübingen, born at Halle in 1839 and died at Schramberg in 1873. Before mentioning the creators of modern synthetic geometry, it will be convenient to call attention to two other divisions of pure mathematics which have been greatly developed in recent years, but any sketch of the results arrived at or the methods by which they have been attained would be so closely connected with the work of living mathematicians that I shall do little more than mention the names of the subjects. Analytical geometry has been studied by a host of modern writers, but I do not propose to describe their investigations, and I shall content myself by merely mentioning the names of the following mathematicians. James Booth, born in the country of Leitrim on August 25, 1806, and died at Buckinghamshire on April 15, 1878, was one of the earliest writers in this century to devote himself to the development of analytical geometry. His chief results are embodied in his work entitled A Treatise on Some New Geometrical Methods. The researches of James McCulloch, professor in Dublin, born near Starbane in 1809 and died in Dublin in October 24, 1846, which include some valuable discoveries in the theory of quadrics, will be found in this collected works edited by Jellett and Houghton, Dublin 1880, see also below, page 496. Julius Plücker, professor after 1836 in Bonn, born at Elberfeld on July 16, 1801 and died at Bonn on May 22, 1868, devoted himself chiefly to the study of algebraic curves, of a geometry in which the line is the element in space, and the theory of congruences and complexes. His equations connecting the singularities of curves are well known. In 1847 he exchanged his chair for one of physics, and his subsequent researches were on spectra and magnetism. An account of his works was published by Klebsch, Gesellschaft der Wissenschaften, Göttingen, 1872, volume 16. The majority of the memoirs on analytical geometry by Cayley and by Henry Smith deal with the theory of curves and surfaces, the most remarkable of those of Ludwig Otto Hess, born at Königsberg on April 22, 1811, and died at Munich, where he was professor in 1874, are on the plane geometry of curves. See the notice of these by F. C. Klein. Of those of Jean-Gaston Darboux, professor in Paris, born at Nimes at 1842, on the geometry of surfaces, and those of Halphen on the singularities of surfaces and on tortuous curves. The singularities of curves and surfaces have also been considered by Hieronymus Georg Suthen, professor at Copenhagen, born in 1839, and by Hermann Caesar Hannibal Schubert, professor at Hamburg, born at Potsdam in 1848. The lectures of the latter have been published by F. Lindemann, 2 volumes, Leipzig, 1875 and 1891. Noether has discussed the theory of tortuous curves, and Klebsch has applied Abel's theorem to geometry. Among more recent textbooks are Klebsch's Vorlesungen über Geometrie, edited by F. Lindemann, and Salmon's Conic Sections Geometry of Three Dimensions, and Higher Plane Curves, in which the chief discoveries of these writers are embodied. Finally, I may allude to the extension of the subject matter of analytical geometry by the introduction of the ideas of space of n dimensions in the writings of Grossman in 1844 and 1862. Among those who have extended the range of analysis, including the calculus and differential equations, or whom it is difficult to place in any of the preceding categories, are the following, whom I place in alphabetical order: Appel, Bertrand, Boole, Cauchy, Darboux. Forsyth, who has written on Pfaff's problem and is also the author of the standard English treatise on differential equations. Frobenius, Lazarus Fuchs, professor at Berlin, born in Prussia 1833, Halphen, Jacobi, Jordan, Königsberger, Sophie Koloweski, professor at Stockholm, born on December 27, 1853 and died February 18, 1891. See the Bulletin des Sciences Mathématiques, volume 15, pages 212 to 220. Lai, Poincaré, Riemann, who wrote on the theory of partial differential equations, Schwarz, Sylvester, and Weierstrass, who has developed the calculus of variations. The writers I have mentioned above mostly concern themselves with analysis. I will next describe some of the more important works produced in this century on synthetic geometry. Modern synthetic geometry may be said to have had its origin in the works of Monge in 1800, Carnot in 1803, and Poncelet in 1822, but these only dimly foreshadowed the great extension it was to receive in Germany, of which Steiner and von Staudt are perhaps the best known exponents. Steiner. Jacob Steiner, the greatest geometrician since the time of Apollonius, was born at Utzendorf on March 18, 1796, and died at Bern on April 1, 1863. His father was a peasant, and the boy had no opportunity to learn reading and writing till the age of 14. He subsequently went to Heidelberg and thence to Berlin, supporting himself by giving lessons. His Systematische Entwicklungen was published in 1832. And at once made his reputation. It contains a full discussion of the principle of duality and of the projective and homographic relations of rows, pencils, etc., based on metrical properties. By the influence of Crell, Jacobi, and the von Humboldts, who were impressed by the power of his work, a chair of geometry was created for Steiner at Berlin, and he continued to occupy it till his death. The most important of his other researches are contained in papers which appeared originally in Crell's journal and are embodied in his Systematische Geometrie, Volume 1, edited by C. F. Geiser, Volume 2 by H. Schroeter. These relate chiefly to the properties of algebraic curves and surfaces, pedals and roulettes, and maxima and minima. The discussion is purely geometrical. Steiner's works may be considered as the classical authority on recent synthetic geometry. Von Staudt. A system of pure geometry quite distinct from that expounded by Steiner was proposed by Carl Georg Christian von Staudt, born at Rothenburg on January 24, 1798, and died in 1867, who held the chair of mathematics at Erlangen. In his Geometrie der Lage, published in 1847, he constructed a system of geometry built up without any reference to number or magnitude, but in spite of its abstract form, he succeeded by means of it alone in establishing the non-metrical projective properties of figures, discussed imaginary points, lines, and planes, and even obtained a geometrical definition of a number. These views were further elaborated in his Bertrand Géométrie de l'âge, 1856 to 1860. This geometry is curious and brilliant, and has been used by Kuhlmann as the basis of his graphical statistics. Among other works on pure geometry, I may refer to the Introduzione ad una teoria geometrica delle curve piane, 1862, and its continuation, Preliminari de una teoria geometrica della superficie, by Luigi Cremona of the Polytechnic School at Rome. As usual, textbooks I may mention: M. Schalz's Traité de géométrie supérieure, 1852, J. Steiner's Vorlesungen über synthetische Geometrie 1867 and L. Cremona's Éléments de géométrie projective, translated into English by C. Lusendorf, Oxford 1885, and Thomas Reyes, Géométrie de l'âge, 3 volumes, 3rd edition. I shall conclude the chapter with a few notes, more or less discursive, on branches of mathematics of a less abstract character and concerned with problems that occur in nature. Closely connected with the subject of modern geometry is the science of graphics, in which rules are laid down for solving various problems by the aid of the drawing board. The modes of calculation which are permissible are considered in modern projective geometry. This method of attacking questions has been hitherto applied chiefly to problems in mechanics, elasticity, and electricity, and it is especially useful in engineering, and in that subject an average draftsman ought to be able to obtain approximate solutions of most of the equations, differential or otherwise, with which he is likely to be concerned, which will not involve errors greater than would have to be allowed for in any case in consequence of our imperfect knowledge of the structure of the materials employed. The theory may be said to have originated with Poncelet's work, but I believe that it is only within the last 20 years that systematic expositions of it have been published. Among the best known of such works I may mention are Graphische Statik by C. Kuhlmann, Zurich, 1875, recently edited by W. Ritter, and the Lesioni di Statistica Grafica by A. Favaro, Padua, 1877, French translation annotated by P. Terrier in 2 volumes 1879 to 85, and the Calcolo Grafico by L. Cremona, Milan, 1879, English translation by T. H. Beer, Oxford, 1889, which is largely founded on Mobius's work. La Statique Graphique by M. Levy, Paris, 4 volumes, 1886 to 88, and La Statistica Grafica by C. Cerotti, Milan, 1888. The general character of these books will be sufficiently illustrated by the following note on the concepts of Kuhlmann's work. Kuhlmann commences with a description of the geometrical representation of the 4 fundamental processes of addition, subtraction, multiplication, and division, and proceeds to evolution and involution, the latter being effected by the use of equiangular spirals. He next shews how the quantities considered, such as volumes, moments, and moments of inertia, may be represented by straight lines, thence deduces the laws for combining forces, couples, etc., and then explains the construction and use of the ellipse and ellipsoid of inertia, the neutral axis, and the kern. The remaining and larger part of the book is devoted to shewing how geometrical drawings made up on these principles give the solutions of many practical problems connected with arches, bridges, frameworks, earth pressure on walls and tunnels, etc. The subject has been treated during the last 20 years by numerous writers, especially in Italy and Germany, and applied to a large number of problems. But as I stated at the beginning of this chapter, that I should as far as possible avoid discussions of the works of living authors, I content myself with a bare mention of the subject. End of section 36. Recording by Paul King, Mississauga, Ontario, pjk.scripps.mit.edu/pkj. Chapter 19, Part 4 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by W. Rouse Ball. Chapter 19. Mathematics of Recent Times, Part 4. Clifford. I may, however, add here a brief note on Clifford, who was one of the earliest English mathematicians of the latter half of this century to advocate the use of graphical and geometrical methods in preference to analysis. William Kingdon Clifford, born at Exeter on May 4, 1845, and died at Madeira on March 3, 1879, was educated at Trinity College, Cambridge, of which society he was a fellow. In 1871 he was appointed professor of applied mathematics at University College London, a post which he retained till his death. His remarkable felicity of illustration and power of seizing analogies made him one of the most brilliant expounders of mathematical principles. His health failed in 1876, when the writer of this book undertook his work for a few months. Clifford then went to Algeria and returned at the end of the year, but only to break down again in 1878. His most important works are his theory of biquaternions, on the classification of loci, unfinished, and the theory of graphs, unfinished, his canonical dissection of a Riemann surface, and the elements of dynamic also contain much interesting matter. I next turn to the question of mechanics treated analytically. The knowledge of mathematical mechanics of solids attained by the great mathematicians of the last century may be said to be summed up in the admirable Mécanique analytique by Lagrange and Traité de mécanique by Poisson, and the application of the results to astronomy is illustrated by Laplace's Mécanique céleste. These works have been already described. The mechanics of fluids is more difficult than that of solids, and the theory is less advanced. Theoretical statics, especially the theory of potential and attractions, has received considerable attention from mathematicians of this century. I have already mentioned that the introduction of the idea of the potential is due to Lagrange, and it occurs in a memoir of a date as early as 1773. The idea was at once grasped by Laplace, who, in his memoir of 1784, used it freely, and to whom the credit of the invention was formerly somewhat unjustly attributed. In the same memoir, Laplace also extended to space of three dimensions the idea of circular harmonic analysis, which had been introduced by Legendre in 1783. Green. George Green was one of the earliest writers of this century who investigated further the properties of the potential. Green was born near Nottingham in 1793 in a humble condition in life, and died at Cambridge in 1841. Although self-educated, he contrived to get access to various mathematical books, and in 1827 wrote a paper on the potential, in which the term was first introduced, proved its chief properties, and applied the results to electricity and magnetism. This contains the important theorem now known by his name. This remarkable paper was seen by some neighbours who were able to appreciate the power shewn in it. It was published by subscription in 1828, but does not seem to have attracted much attention at first. Similar results were independently established in 1839 by Gauss, to whom their general dissemination was due. In 1832 and 1833 Green presented papers to the Cambridge Philosophical Society on the equilibrium of fluids and on attractions in space of n dimensions, and in the latter year his memoir on the motion of a fluid agitated by the vibrations of a solid ellipsoid was read before the Royal Society of Edinburgh. In 1833 he entered at Caius College, Cambridge, and was subsequently elected to a fellowship. He then threw himself into original work, and produced in 1837 his paper on the motion of waves in a canal, and on the reflection and refraction of sound and light. In the latter, the geometrical laws of sound and light are deduced by the principle of energy from the undulatory theory, the phenomenon of total reflection is explained physically, and certain properties of the vibrating medium are deduced. He also discussed the propagation of light in any crystalline medium. Of Gauss's work on attractions I have already spoken. The theory of level surfaces and lines of force is largely due to Chasles,
who also determined the attraction of an ellipsoid at any external point.
I ought not to leave the subject of theoretical statics without mentioning Mobius. August Ferdinand Mobius, professor at Leipzig, who was born at Schulpforta on November 17, 1790 and died on September 26, 1868, was one of the best known of Gauss's pupils. He published his Barycentrisches Calcul in 1826. His collected works were published at Leipzig in 4 volumes, 1885 to 1887. Among living writers I may allude to Sir Robert Stawell Ball, Lowndean professor in the University of Cambridge, born in Dublin on July 1, 1840, who issued his Theory of Screws in 1876. Theoretical dynamics has been studied by most of the writers above mentioned. In addition to these, I may repeat that the principle of varying action was elaborated by Sir William Hamilton in 1827, and the Hamiltonian equations were given in 1835, and I may call attention to Bertrand's work on dynamics. The use of generalized coordinates introduced by Lagrange has become the customary means of attacking dynamical as well as many physical problems. The standard English textbook on the dynamics of rigid bodies is that by Dr. Rouse. On the mechanics of fluids, liquids, and gases, apart from the physical theories on which they rest, I propose to say nothing except to refer to the memoirs of Green, Sir George Stokes, Lord Kelvin, better known as Sir William Thomson, and von Helmholtz. The fascinating but difficult theory of vortex rings is due to the 2 writers last mentioned. One problem in it has been also considered by J. Thomson, but it is a subject which is as yet rather beyond our powers of analysis. The subject of sound may be treated in connection with hydrodynamics, but on this I would refer the reader who wishes for further information to the work published at Cambridge in 1877 by Lord Rayleigh, recently Cavendish Professor in the University of Cambridge. Theoretical astronomy is included in, or at any rate closely connected with, theoretical dynamics. Among those who in this century have devoted themselves to the study of theoretical astronomy, the name of Gauss is one of the most prominent. To his work I have already alluded. Bessel. The best known of Gauss's contemporaries was Friedrich Wilhelm Bessel, who was born in Minden on July 22, 1784, and died at Königsberg on March 17, 1846. Bessel commenced his life as a clerk on board ship, but in 1806 he became an assistant in the observatory at Lilienthal, and was thence in 1801 promoted to be director of the new Prussian observatory at Königsberg, where he continued to live during the remainder of his life. Bessel introduced into pure mathematics those functions which are now called by his name. This was in 1824, though their use is indicated in a memoir 7 years earlier, but his most notable achievements were the reduction, given in his Fundamenta Astronomiae, Königsberg 1818, of the Greenwich observations by Bradley of 3,222 stars, and his determination of the annual parallax of 61 Cygni. Bradley's observations have been recently reduced again by Dr. A. Auwers of Berlin. Leverrier. Among the astronomical events of this century, the discovery of the planet Neptune by Leverrier and Adams is one of the most striking. Urbain Jean-Joseph Leverrier, the son of a petty government employee in Normandy, was born at Saint-Lô on March 11, 1811, and died at Paris on September 23, 1877. He was educated at the Polytechnic School, and in 1837 was appointed as lecturer on astronomy there. His earliest researches in astronomy were communicated to the Academy in 1839. In these he calculated, within much narrower limits than Laplace had done, the extent within which the inclinations and eccentricities of the planetary orbits vary. The independent discovery in 1846 by Leverrier and Adams of the planet Neptune, by means of the disturbance it produced on the orbit of Uranus, attracted general attention to physical astronomy, and strengthened the opinion as to the universality of gravity. In 1855 Leverrier succeeded Arago as director of the Paris Observatory and reorganized it in accordance with the requirements of modern astronomy. He now set himself the task of discussing the theoretical investigations of the planetary motions and of revising all tables which involve them. He lived just long enough to sign the last proof sheet of this work. Adams. The co-discoverer of Neptune was John Couch Adams, who was born in Cornwall on June 5, 1819, educated at St. John's College, Cambridge, subsequently appointed to Lowndean professor in the university, and director of the observatory, and who died at Cambridge on January 21, 1892. There are three important problems which are especially associated with the name of Adams. The first of these is his discovery of the planet Neptune from the perturbations it produced on the orbit of Uranus. In point of time, this was slightly earlier than Leverrier's investigation. The second memoir to which I referred was on the secular acceleration of the moon's mean motion. Philosophical Transactions, 1855, volume 143, page 377. Laplace had calculated this on the hypothesis that it was caused by the eccentricity of the Earth's orbit, and had obtained a result which agreed substantially with the value it deduced from a comparison of the records of ancient and modern eclipses. Adams shewed that certain terms in an expression had been neglected, and that if they were taken into account the result was only about one half that found by Laplace. The correctness of the calculations of Adams was denied by Plana, Pontécoulant, and other continental astronomers, but Delaunay in France and Cayley in England verified the work. The third investigation connected with the name of Adams is his determination of the orbit of the Leonids or shooting stars, which were especially conspicuous in November 1866, and whose period is about 33 years. Newton of Yale had shewn that there were only 5 possible orbits. Adams calculated the disturbance which would be produced by the planets on the motion of the node of the orbit of a swarm of meteors in each of these cases, and found that this disturbance agreed with the observations for one of the possible orbits, but for none of the others. Hence the orbit was known. Other well-known astronomers of this century are Giovanni Antonio Amadeo Plana, born at Voghera on November 8, 1781, and died at Turin on January 20, 1864, whose work on the motion of the moon was published in 1832. Philip Gustave Dulcet, Count Pontécoulant, born in 1795 and died at Pontécoulant on July 21, 1871. Charles Eugène Delaunay, born at Lausigny on April 9, 1816, and drowned off Cherbourg on August 3, 1872, whose work on the lunar theory indicates the best method yet suggested for the analytical investigations of the whole problem, and whose incomplete lunar tables are among the astronomical achievements of this century. And Peter Andrew Hansen, born at Schleswig on December 8, 1795, and died at Gotha, where he was head of the observatory on March 28, 1874, who compiled the lunar tables published in London in 1857, and celebrated the most delicate methods yet known for the determination of lunar and planetary perturbations. For an account of his numerous memoirs, see the Transactions of the Royal Society of London for 1876 to 1877. Among living mathematicians I may mention the following names. Félix Tisserand of Paris, born in 1845, whose Mécanique Céleste forms a worthy pendant to Laplace's work of the same title. George William Hill, born in New York in 1838 and until recently on the staff of American Ephemeris, who in 1884 determined the inequalities of the moon's motion due to the non-spherical figure of the Earth, an investigation which completed Delaunay's lunar theory. Hill also dealt with the secular motion of the moon's perigee and the motion of a planet's perigee under certain conditions, and he has written on the analytical theory of the moon of Jupiter and Saturn with a view to the preparation of tables of their positions at any given time.
Simon Newcomb, born in Nova Scotia on March 12, 1835, superintendent of the American ephemeris, who re-examined the Greenwich observations from the earliest times, applied the result to the lunar theory, and revised Hansen's tables. George Howard Dowron of Trinity College, Cambridge, born in Kent in 1845, now Plumian professor in the University of Cambridge, who has written on the effect of tides on viscous spheroids, the development of planetary systems by means of tidal friction, the mechanics of meteoric swarms, etc. Perhaps also I may here mention Poincaré, who has discussed the difficult problem of three bodies and the form assumed by a mass of fluid under its own attraction. Within the last half-century, the results of spectrum analysis have been applied to determine the constitution and directions of motions of the heavenly bodies to and from the Earth. The early history of spectrum analysis will be always associated with the names of Gustav Robert Kirchhoff and A. J. Angstrom of Uppsala and Sir George Stokes of Cambridge, but it pertains to optics rather than to astronomy. Within the last few years, the range of astronomy has been still further extended by the art of photography. To what new developments this may lead, it is as yet impossible to say. Mathematical physics. An account of the history of mathematics in this century would not be other than misleading if there were no reference to the application of it to numerous problems in heat, elasticity, light, electricity, and other physical subjects. The history of mathematical physics is, however, so extensive that I could not pretend to do it justice even were its consideration properly included in a history of mathematics. Moreover, it is so closely connected with the works of living physicists, notably of von Helmholtz and of Lord Kelvin, better known as Sir William Thomson, that I may consider it outside the limits I have laid down for myself in this chapter. It is, however, interesting to note that the advance in our knowledge of physics is largely due to the application to it of mathematics, and every year it becomes more difficult for an experimenter to make any mark on the subject unless he is also a mathematician. Amongst recent writers on mathematical physics, excluding all reference to experimental physics, as also to theories to which mathematical analysis has not yet been applied, I may specially mention the following, whose names are here arranged alphabetically, though the list does not in any way profess to be complete or exhaustive. J. Boussinesq of Paris, who has written on optics. Ludwig Boltzmann of Vienna, whose writings greatly extended the kinetic theory of gases and have done something to bring the molecular physics within the domain of mathematics. Rudolf Julius Emanuel Clausius, born at Köslin on January 2, 1822, and died at Bonn, where he was professor of physics in August 1888, who was among the earliest to discuss the subject of heat from a mathematical point of view. Clebsch, who discussed the elasticity of solid bodies. Julius Wilhelm Richard Dedekind, who is the author of a remarkable memoir on the vibrations of a liquid ellipsoid, which is treated as a problem in pure mathematics. Michael Faraday, born at Newington on September 22, 1791, and died at Hampton Court on August 25, 1867, who had a special gift in deducing results by general reasoning from fundamental principles, and in disentangling those principles from the symbols in which they are usually expressed. For further details, see the biographies of Tyndall, 2nd edition 1870, Bence-Jones 1870, or Dr. Gladstone 1872. George Francis Fitzgerald, professor in Dublin, born there on August 3, 1851, who has written on electromagnetism and optics. John Bernard Léon Foucault, born at Paris on September 18, 1819, and died there of paralysis on February 11, 1868, whose chief memoirs were on the predictability of photography, 1840,
on the electric lamp 1849, on the determination of the velocity of light in 1850, but repeated with improvements in 1862. On his demonstration of the diurnal motion of the earth by means of the rotation of the plane of oscillation of a simple pendulum 1851, on the gyroscope 1852, on the rotation of a copper disc between the poles of a magnet 1855, and on a polarizer 1857. For further details see La vie et travaux de Léon Foucault by J. A. Lycejus, Paris, 1875, and also a notice by J. Bertrand, preface to the collected edition of Foucault's works, Paris, 1878. J. Willard Gibbs of Yale, America, who has written on the thermodynamics and Maxwell's electromagnetic theory. Richard Tetley Glazebrook of Trinity College, Cambridge, born at Liverpool on September 18, 1854, who has written on optics and electricity. His report in the Transactions of the British Association 1885 on theories of optics contains a valuable summary of most of the mathematical researches on that subject during this century and prior to the date of the report. After a brief allusion to the views of Green, Cauchy, McCulloch, and F. E. Newman, he describes the more recent work according as it comes under the simple elastic solid theory, or theories assuming an action between matter and ether, or Maxwell's electromagnetic theory. Green, whose physical memoirs were mostly on the theory of waves. Von Helmholtz, who is in the front rank of all departments of mathematics and physics. His collected papers were published in 2 volumes, Leipzig, 1882 to 1883. Oliver Heaviside, who has written on the mathematical theories of optics and electromagnetism. Lord Kelvin, or Sir William Thomson, professor at Glasgow, born at Belfast, June 1824, who has enriched every department of physics by his researches. His collected papers were published at Cambridge, Volume 1 in 1882, and Volume 2 in 1884, and Volume 3 in 1890. Gustav Robert Kirchhoff, professor in physics, first at Heidelberg and then at Berlin, born at Königsberg on March 12, 1824, and died in Berlin October 17, 1887, whose name will always be associated with the history of spectrum analysis and his researches on elasticity. His collected papers were published at Leipzig in 1882. Gabriel Lamé, born at Tours on July 22, 1795, and died at Paris in 1870, where he was professor at the Polytechnic School, whose best-known works are his Course on Physics, 1836, his Treatise on Elasticity, 1852, his work on Functions, 1857, an essay on the curvilinear coordinates, 1859, and lastly his Theory of Heat, 1861. He also wrote memoirs on different points in the theory of numbers. James Clerk Maxwell, born at Edinburgh on June 13, 1831, and died at Cambridge on November 5, 1879, where he was professor of experimental physics. His most important works were his memoir in 1859 on the stability of Saturn's rings, various articles on color, his memoir on the electromagnetic field, his Electricity and Magnetism issued in 1873, his Theory of Heat published in 1871, and his elementary textbook on matter and motion. To these I may add his memoir on reciprocal figures, which are useful in graphics, and his papers on molecular theory of gases and cognate subjects. His Electricity and Magnetism has revolutionized the treatment of the subject. Poisson and Gauss had explained the phenomenon of electrostatics by attraction and repulsions between imponderable particles, while Lord Kelvin, Sir William Thomson, in 1846 has shewn that the effects might be supposed analogous to a flow of heat from various sources of electricity properly distributed. In electrodynamics, the theory then generally current was that proposed by W. E. Weber, in which the attraction between electrified particles depends on their relative motion and position. Maxwell rejected all these hypotheses and explained the phenomenon by stresses and motions of a material medium. He concluded by shewing that if the medium were the same as the so-called luminiferous ether, the velocity of light would be equal to the ratio of the electromagnetic and electrostatic units. Subsequent experiments have tended to confirm this conclusion. For fuller details, his collected works, Cambridge, 2 volumes, 1890, and his Life by L. Campbell and W. Garnett, London, 1882, may be consulted. McCulloch, who wrote on physical optics. Franz Ernst Neumann of Königsberg, born at Uckermark on September 11, 1798, who wrote on elasticity and light. William John Rankine of Glasgow, born at Edinburgh on July 5, 1820, and died December 24, 1872, whose discoveries in thermodynamics and hydromechanics will be found in the collected edition of his works issued in London in 1881. Lord Rayleigh, born on November 12, 1842, who, besides some classical papers on the mathematics of physical optics, has written the standard English work on sound, published at Cambridge in 1877. Barré de Saint-Venant, whose researches on elasticity and torsion are well known. Sir George Gabriel Stokes, most of whose papers on hydromechanics or optics or allied subjects, these memoirs have been recently collected and published by the University of Cambridge. Peter Guthrie Tait, professor in Edinburgh, born at Dalkeith on April 28, 1831, who has written on the mathematics of various physical subjects, and especially on the molecular theory of gases. Joseph John Thomson, of Trinity College and Cavendish professor in the University of Cambridge, born at Manchester on December 18, 1856, who has written on vortex rings and the application of generalized coordinates to various physical problems. I may also allude to his report on the Transactions of the British Association, 1885, on electric theories, which he classifies into those not founded on the principle of conservation of energy, such as those of Ampere, Grassmann, Stefan, and Korteweg; those which rest on assumptions concerning the velocities and positions of electrified particles, such as those of Gauss, W. E. Weber, Riemann, and Clausius; those which require the existence of a kind of energy of which we have no other knowledge, such as the theory of C. Neumann; those which rest on the dynamical considerations but in which no account is taken of the action of the dielectric, such as the theory of F. E. Neumann; and finally those which rest on the dynamical considerations and in which the action of the dielectric is considered, such as Maxwell's theory. In the report these theories are described, criticized, and compared with the results of experiments. Wilhelm Eduard Weber died in 1891, whose most important investigations were in connection with electrodynamics. His works are being produced by the Royal Society of Göttingen, Volume 1, edited by W. Voigt, Berlin, 1892. And Gustav Heinrich Wiedemann of Bale, born October 2, 1826, who is the author of an admirable textbook on electricity and allied subjects, 4 volumes, 1882 to 1885. I am well aware that the above list excludes many who have studied physics from a strictly mathematical point of view, and I give it not as an account of a contemporary work, but as a pendant to this chapter, which may serve as an indication of the subjects discussed by many mathematicians in recent times, illustrated by the names of a few of them. To make it more than this would involve the knowledge to which I can make no pretense. End of Part 37. Reading by Paul King, Mississauga, Ontario. pjk.scripps.mit.edu/pkj. This is the end of a short account of the history of mathematics by W. W. Rouse.